Good afternoon and good morning, everyone. Thank you for joining us for today's workshop. We are going to get started here in just about 8 minutes, but before we do, I would like to go over a few housekeeping items with those of you that have already come into the room. For those of you that have already joined us, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod is the best way to communicate with us should you have any questions regarding today's material. So please feel free at any point of all of the presentations today to go ahead and type in your questions there in the chat pod, and we will house them and either get them answered directly after the presentation if we have time, or we will hold all of the rest of the questions until our panel discussion. We'll have about a 30-minute panel discussion at the end of all of the presentations today. So please make sure that you do type in your questions, and we will do everything that we can to make sure that they are posed to our presenters and they get answered. Now, this chat pod is also the best way to communicate with us should you experience any technical issues. If you do have any technical issues, please let us know there in the chat pod, and either myself or one of our customer service representatives will make sure to get you taken care of. A few common technical issues that might occur, or you might lose your audio, or you might lose your live feed. If this should happen, the best thing to do is simply refresh your web browser that you are viewing the event in, and then simply click the play button again on the live feed. This should refresh your connection and allow you to continue on. If for some reason your chat pod is not functioning properly or you need further assistance, we do have our customer service contact information up above the live feed. We have our phone number as well as our email address. So if you do need to get in touch with us and are not able to utilize the chat pod for whatever reason, we do have other avenues for you. We've got about 5 or 6 minutes before we do get started. So at this time, I would like to ask that all of our participants that have come into the room to go ahead and utilize that chat pod and type in your location. That way we can find out just where our audience is joining us from today, as well as what kind of reach we were able to obtain with today's workshop. Again, we've got a few minutes before we get started. I'm going to mute my line, but I will come on once more to go through housekeeping again, and then we will get started at the top of the hour. Thank you for joining us today. Good morning and good afternoon, everyone. Thank you for joining us for today's workshop. We are going to get started here in about 2 minutes, but before we do, I would like to go over a few housekeeping items with those of you that have just joined us in the room. For those of you that did just log in, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. I see quite a few of you have already found this. This chat pod is going to be the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained, and we will either get them asked directly after the presentation if we have time, or we will hold them all until our panel discussion Q&A session that we will have after all four presenters have presented their topics. We will have probably about 30 minutes at the end of today's event to have a panel discussion, so please feel free at any point of any of the discussions and presentations today to go ahead and type in your questions there in the chat pod, and we will pull them out and house them for you. We would hate for any questions to be forgotten or to get lost in the shuffle. This chat pod is also the best way to communicate with us should you experience any technical issues. If you do have any technical issues, please make sure to let us know there in the chat, and either myself or one of our customer service representatives will make sure to get you taken care of. Some common technical issues that might occur are you might lose your live feed or your live audio. Should this happen, simply refresh your web browser and then hit the play button on your live feed again. Most of the time this will refresh your connection and you can continue on with the workshop. If for some reason you are not able to get in contact with us through the chat pod, we also have our customer service contact phone number and email address directly above the live feed. So if you are not able to access the chat or are having any other technical issues, please feel free to use one of those outlets as well. It is the top of the hour, but before we do get started, as some of you have already done, if those of you that did just join us could type in your location in the chat pod, that'll give us some great feedback about our audience and who has joined us today and where you are watching today's workshop from. Again, it is the top of the hour, so I'm going to go ahead and mute my line back. We'll switch up a few things, and then we will get started here momentarily. Thank you for joining us today. Good morning and good afternoon, everyone. Thank you for joining us for today's workshop. My name is Josh Vickers, and I'm with RTI International's Forensic Technology Center of Excellence. Today's workshop is Workshop 8, and our final workshop in the Probabilistic Genotyping workshop series. Today's topic of discussion is Probabilistic Genotyping Summation and other special topics. We do have 4 presenters today. But I'm going to first introduce Dr. Tamara Moretti, who has been the moderator and champion behind this entire workshop series. Dr. Tamara Moretti is with the FBI laboratory. She's developed this series as a forum for experts in the field of statistical genetics and probabilistic genotyping to share their knowledge and experience as the forensic DNA testing community transitions to ProbGen. She will be moderating today's event. But before we hand things over, just a quick disclaimer. The opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. And now, without any further ado, I would like to hand things over to our moderator for today's event, Dr. Tamara Moretti. Tamara?
Thank you so much, Josh, and I'd like to welcome and thank you all for returning to our last session here in our web series on probabilistic genotyping. Today we have 4 speakers lined up. We had originally thought this session would be a good place to have a panel discussion and overflow of questions and such, but we actually, as the course evolved, came up with some additional topics that we thought would be very useful to present to you. So on the left side of my screen, We have the speakers listed, and I will introduce them in a moment, but we're also very pleased that Peter Gill, Geraldine Conway, and David Kay have rejoined us. So they're on the line as well today to contribute to the discussion. That if you all have questions, and I invite you all of our speakers here today to speak up and share in this discussion. We're going to have 4 talks today, and the first is going to be by Dr. Joanne Bright, who's going to be speaking on, I think, one of the most difficult topics relating to probabilistic genotyping, and that is the data that are LRs that are close to 1. And then we're going to be following up with John Buckleton, who was in court on his scheduled slot a couple modules ago, to talk about admissibility issues related to probabilistic genotyping. We're going to have a brief break at that point and then continue with Ted Hunt, who's going to be speaking about what we have sort of termed the role of the DNA examiner relative to probabilistic genotyping. And then Klaus Sluten had offered to share some information that he has, some work that he's done related to the question of LRs, what happens when a person of interest is identified through a database search. So I'd like to introduce all of our speakers. First, Dr. Joanne Bright. She is a senior science leader at the Institute of Environmental Science and Research Limited, ESR, in New Zealand, where she's worked since 1999. She completed her Bachelor of Science degree at Victoria University of Wellington in 1998 and her Master of Science in Forensic Science at the University of Auckland in 2000. In 2015, Jo was awarded her PhD after studying advanced DNA profile interpretation topics. She's co-authored over 70 peer-reviewed papers and presented at a number of workshops and conferences in this area, including in the US, UK, Asia, and Europe. She is one of the co-developers of StarMix, which is an expert software we've heard about for interpreting forensic profiles. And in 2018, StarMix was awarded the New Zealand Prime Minister's Science Prize for their contribution to science in New Zealand and internationally. So thank you so much, Jo, for joining us today, and welcome. After Jo, Dr. John Buckleton will be speaking. He is a forensic scientist for the Government of New Zealand, specializing in DNA interpretation, firearm scenes, and general forensic casework in the laboratory. His experience covers 35 years in the UK, USA, Australia, Netherlands, and New Zealand, where he's examined over 2,000 cases and testified possibly over 200 times, including in New Zealand, Australia, England, the Netherlands, and the US. He's co-authored over 200 significant publications in the forensic field in a variety of different disciplines. He lectures at the University of Auckland, Department of Statistics, and from 1988 to present has presented DNA and glass courses to practicing forensic professionals, scientists in the UK, USA, Australia, Asia, and New Zealand. He's supervised 5 PhD students in the field of forensic interpretation and has been involved in international research and development programs in the area of the forensic interpretation of glass and DNA, including expert systems. He is also a co-developer of the probabilistic genotyping software StarMix. Following John, we will hear from Ted Hunt. He is a senior advisor to the Attorney General on forensic science at the Department of Justice. In that capacity, he serves as the department's lead advisor on all issues involving forensic science policy and practice. Prior to this appointment, Mr. Hunt was chief trial attorney at the Jackson County Prosecutor's Office in Kansas City, Missouri, where he served for over 26 years as a state-level prosecutor and managed a large staff of trial attorneys. During that time, he prosecuted well over 100 felony jury trials, most of which involved litigation of forensic evidence. He is a former member of the National Commission on Forensic Science, the ASCLD Lab Board of Directors, the Missouri Crime Lab Review Commission, and the OSAC Legal Resource Committee. He is as well a fellow of the Jurisprudence section of the American Academy of Forensic Sciences. And also returning with us today is Dr. Klaus Slooten, who is currently working at the Netherlands Forensic Institute, where he has held a position as a statistician and as a reporting officer in kinship cases. In addition, he is an endowed professor at the VU University of Amsterdam for forensic genetics at the Department of Mathematics. His interests lie in giving mathematical description to problems in forensic genetics, usually in kinship analysis and mixture analysis, but also generally. One of his current activities is the statistical modeling of DNA mixture profiles. Amongst other things, he's devised and programmed a semi-continuous model for the evaluation of LRs for DNA mixtures that is detailed in the references that we have provided on the website. Dr. Slooten studied mathematics in Leiden in the Netherlands and obtained a PhD from the University of Amsterdam in 2003. Since 2008, he has worked at the NFI, and his research and publications there are concerned with DNA databases, familial searching, the effect of uncertainty on the weight of evidence, DNA mixtures, and the theory and philosophy of statistical evidence for forensics. He's currently writing a book on forensic statistics that is due to appear next year, and he also teaches regularly at the VU University and has a course on forensic probability and statistics for mathematics students, another one on statistics in general, and he also teaches DNA statistics at NFI. So you can see we have a great group of speakers for you today, and I welcome and thank them all for contributing to our efforts here. And with that, I would like to invite Dr. Bright to begin sharing her screen and presentation. Thanks so much for being with us today.
Thanks, Tamara, and thanks to the audience for tuning in. As Tamara said, I have been asked to talk about low-level likelihood ratios. In the last few years, I've had the opportunity to talk to hundreds of forensic biologists around mostly America, but also Australia and in Europe. And from these conversations, I've compiled some of the major concerns that analysts might have about reporting low-level LRs. In this talk, I plan to address the concern that low likelihood ratios represent an increased risk of an adventitious match, that low LRs risk flip-flopping from supporting one proposition to then supporting the alternate proposition, and that likelihood ratios for low-level mixtures are difficult to explain in court. My talk really draws on my experience as a caseworker and my research interests and focuses more on the biology. Sadly, I'm probably going to disappoint the likes of Klaus and any other academics and statisticians in the audience. I plan as much as I can to avoid maths and formulas. So I'm going to start with a confession as well. So in my 20-year career as a forensic scientist, I've only ever reported likelihood ratios. So unlike many of you, I've not had to transition to using likelihood ratios from a different method, such as the CPI or RMP. My second confession, as Tamara said, this is a difficult topic. I don't claim that I have all the answers. These are some of the hardest topics because everyone seems to have an opinion, and sometimes there's conflicting advice in the scientific publications. But I trust that you can weigh up those opinions and advice, and you can make sound judgments for yourselves. So let's begin. I'm going to start with a really simple example of a single locus profile from a single contributor. The genotype is an unambiguous 1415, and we can see that our person of interest is also a genotype 1415, and we can conclude that they are not excluded as a possible contributor. We want to assign a likelihood ratio, and for this we need a set of propositions. The best prosecution proposition for this case is that the DNA has originated from the person of interest, and the best defense proposition, given the limited information we have, is that the DNA has originated from someone else who is unrelated to the person of interest. So we have the probability of the evidence given the prosecution proposition divided by the probability of the evidence given the defense proposition. I've used HP, where P is the prosecution, and HD, where D is the defense. But of course, you can insert whatever nomenclature you'd like here. There are also other propositions available that we could consider depending on the case circumstances. But the probability of the evidence given the prosecution proposition is 1 in this case. The evidence is fully explained by the person of interest being a contributor. Under the defense proposition, we explain the DNA as originating from an unknown individual unrelated to the person of interest. And this is estimated by our allele frequencies. I'm using the product rule as a simplification, of course, but in casework would be applying a subpopulation correction in the form of theta. In this slide, I'm just going to focus on the denominator of the likelihood ratio. This is the probability of the evidence given it has originated from a random man, or the random match probability. The random match probability is the probability of an unrelated person randomly picked from the relevant population matching the evidence genotype. In simple cases like this one, where the numerator is 1, the denominator of the likelihood ratio is simply the RMP. So going back to my example, assuming my allele frequencies are 0.14 for the 14 allele and 0.25 for the 15 allele, my likelihood ratio is approximately 14. I would report that the evidence is 14 times more likely if it had originated from the person of interest than if it had originated from another individual from the relevant population who is unrelated to the person of interest. So I think we can agree that this likelihood ratio is low, but I suspect this is not the type of low likelihood ratio people are concerned about. I think people are more concerned about low likelihood ratios arising from the interpretation of mixed and complex DNA profiles, not unambiguous single locus, single source profiles like this one. But everything else following in this presentation applies to both types. So, for this example, 7% of the population would be expected to have genotype 1415, and therefore would have a likelihood ratio that would be the same as our person of interest. Comparison of the evidence profile to someone else not our person of interest, who was genotype 1415, would lead to what we call an adventitious match. Sometimes these adventitious matches are erroneously called false positives or false inclusions. I've also heard some people call them errors. These are not false or an error. They are an expectation in forensic biology due to our population genetics. They're not a new concept either, introduced by probabilistic genotyping methods. It also applies mixed DNA profiles, not just single source, obviously, where if a random individual shares sufficient alleles by chance with the mixture, that can lead to a likelihood ratio greater than 1 for that individual. And therefore, that would support their inclusion as a possible contributor to the profile. So we have reported the rates of adventitious matches for star mix in this 2018 paper, describing the internal validation of star mix for 31 laboratories. In this work, we presented the results of both sensitivity and specificity experiments for 2,825 3, 4, and 5-person mixed DNA profiles. These profiles were from a range of different kit types for a range of different mixture types, including different mixture proportions and different total amounts of DNA. For the sensitivity studies, we assigned a likelihood ratio for all known contributors to all 2,800 plus mixtures. And as part of the specificity studies, we assigned likelihood ratios for 10,000 non-contributors, leading to over 28 million non-contributor likelihood ratios. Here's a table summarizing the counts of the non-contributor comparisons, resulting in likelihood ratios of 2 or more. Over 28 million of the comparisons resulted in likelihood ratios less than 1, that is in support of the alternate proposition or exclusionary LRs. But 90,000 gave a likelihood ratio greater than 2, or inclusionary likelihood ratios. And these are adventitious matches. The highest likelihood ratio for a non-contributor was 505,000, and that non-contributor, that individual, shared 81% of their alleles by chance with the mixture. In the third column of this table, I've given the observed frequency of non-contributor LRs, given the defined range there in the first column. So 505,000 sounds high, but what would be the expectation? Alan Turing has showed us that if the model is behaving correctly, the expected likelihood ratio for a false proposition is 1. So that is, the average likelihood ratios for non-contributors should equal 1. And those of you who aren't familiar with Alan Turing, he was a very famous British mathematician. He was also a pioneer of computer science, probably best known for his work in World War II, where he was part of the team that cracked the German Enigma code. And it was just this week in our and the proof of this published in these 2 publications, authored by John Buckleton, Duncan Taylor, Ian Everett, and James Curran. And it's also been demonstrated for the 31 laboratory compilation data set, where the average over the 28 million non-contributor likelihood ratios was 0.12. This average is below 1, most likely due to the use of the Balding and Nichols population genetic model within StarMix, what's called the NRC2 4.2 in the US. This model is known to be conservative. In addition, we use a conservative value of theta of 1% for Caucasians. That same theory from Alan Turing leads to the observation that the probability of observing a likelihood ratio the same or larger for an unrelated non-contributor as for the person of interest is less than or equal to 1 over that likelihood ratio. That's a little bit hard to get your head around. So let's go back to the example. The probability of observing this likelihood ratio or larger for a non-contributor is less than or equal to 1 over 14. If your likelihood ratio is 1 million, the probability of observing a likelihood ratio of 1 million or more for a non-contributor would be less than or equal to 1 in a million. And that's irrespective of whether your numerator is 1. So here are the results again from the 31 lab compilation. Based on the theory from Alan Turing, I've included the expected frequency of the non-contributors given that defined range. And we can see that the observed frequencies in the third column are always less than the expected frequencies, which are given there in the fourth column. and that is for all categories or all likelihood ratio ranges provided. So this demonstrates good performance of the models within StarMix. So moving on to the question of whether low-level likelihood ratios are reliable, we can use the results of sensitivity and specificity testing to answer this. I'm just going to define them there. Sensitivity studies demonstrate the range of likelihood ratio values that can be expected for known contributors, so these are true contributors, and specificity studies should demonstrate the range of likelihood ratio values that are expected for non-contributors. And the experiments should be conducted over a range of mixture types, those that you encounter within your forensic casework. We vary the number of contributors, we vary the mixture proportions, and the DNA template. In 2014, Duncan Taylor published some early sensitivity and specificity data for a number of mixed DNA profiles that were amplified in Global Filer and were interpreted in StarMix. I'm going to show you one set of the results from this work, but there's the reference where you can find more if you're interested. So here is the results from 10 4-person mixed DNA profiles that Duncan has analysed. Likelihood ratios have been calculated for all the known contributors and also for 186 non-contributors as part of the specificity studies. Duncan has plotted the log of the likelihood ratio on the vertical axis against the DNA in picograms for each contributor on the x-axis. The likelihood ratio for the known contributors is given in green, and those shaded polygons show the coverage of the data points. The likelihood ratio for the non-contributors is that pinky red colour, and again, he's added the polygons to indicate coverage. In this plot, Duncan has demonstrated that the log likelihood ratio for known contributors, these are also called HP true experiments, should be high when template amounts are high, and they should trend to 0 as less information is present within the profile. And on the flip side, we see that the log likelihood ratio for non-contributors, these are sometimes called HD true tests, these trend upwards towards 1 with less information. And in the context of mixed DNA profiles, information includes the amount of DNA from the contributor, the availability of conditioning profiles. For example, if you assume if you assume the donor's profile on their intimate samples, then we're adding information. Replicate PCRs also add information, and decreasing the number of contributors, obviously, the fewer the number of contributors to the profile, the more information we have. We can see at very low input amounts in this plot, the likelihood ratio for some known contributors is less than 1, and there are some inclusionary likelihood ratios for the non-contributors. And those inclusionary LRs for the non-contributors, they are the adventitious matches that I was describing, and these are expected. Overall, this plot demonstrates the expected results. At the lower end of input DNA, the results are considered uninformative, in that they don't have the information, or they don't provide the analyst a result that informs them that one proposition is supported over the other. Now, this doesn't mean that the results are unreliable. In fact, we would argue that the opposite is true. It is very reliably giving an uninformative likelihood ratio. Precision studies, they're also going to help us give us confidence in our low-level likelihood ratios. Here I have plotted the likelihood ratio for one contributor interpreted 10 times within StarMix. So this is a 2-person mixture. This is the likelihood ratio for the minor contributor interpreted 10 times. The likelihood ratio there we can see is around 6. That is the likelihood ratio, not the log. And continuous DNA interpretation methods like StarMix that use Monte Carlo Markov chain techniques have this level of non-reproducibility due to the sampling method based on the random number generator. Therefore, the likelihood ratio can differ each time the same sample is interpreted, but we can see in this first plot here that it doesn't change much across the 10 replicates. This next sample is a 3-person mixture, and these bottom 2 are 4-person mixtures, so I've calculated the likelihood ratio for the minor contributor to each of those profiles. Again, you can see that the values don't change much between the replicates. We do see some variability, but certainly nothing that would change the overall conclusion of the analyst. So this variation between replicate interpretations or repeated interpretations doesn't make the results unreliable. In actual fact, we can take into account the variability within our biological and our mathematical models that we use to interpret the profiles. And that variability due to MCMC isn't the only variability we can model. There's also variability in our allele frequency estimates. Of course, they're just a sample. Our value for theta, the number of contributors assigned to the profile, that's also an estimate. Within StarMix, we use the highest posterior density method to calculate the credible interval, and then we can report a lower bound on this interval. So here are the same 4 profiles as before, but now I've plotted the 99% lower bound on the HPD there in orange. You can see that by taking into account uncertainty due to our allele frequencies and the MCMC methods, in this case, the likelihood ratio is lowered, not significantly. We can also use simulation testing to explore the range of expected likelihood ratios. So we do this by simulating thousands or millions of random individuals based on allele frequencies, and we can assign the likelihood ratio considering each one of them is a person of interest. We can then plot the distribution of those likelihood ratios. So here is an example of that. In this plot, I've used the program DBLR to simulate 100,000 random individuals, and then I've assigned the likelihood ratio, assuming they are the trace contributor, to a 4-person mixture. The y-axis gives the proportion of the 100,000 random individuals given the log base 10 of the likelihood ratio on the x-axis. The plot shows that the bulk of the area sits just to the left of a log likelihood ratio of 0, or a likelihood ratio that is inconclusive. So sitting just to the left, the bulk of them are exclusionary LRs. This type of HD true testing is quite common. It can help answer the question, what is the expected range of likelihood ratios for a non-contributor? And just out of interest, in this example, the likelihood ratio for the known contributor, that 4th contributor to this 4-person mixture, is 50. In this next plot, I've given the likelihood ratio for the same 100,000 non-contributors, but I've also plotted 100,000 known contributors there in blue. So this is a different type of simulation testing. We've sampled from the accepted genotypes for the trace 4th contributor according to how probable their genotypes are, and we've assigned a likelihood ratio assuming they are a true contributor. Again, we see a range of likelihood ratios. This time it's mostly to the right of a log likelihood ratio of 0. This type of testing would help an analyst see the range of expected likelihood ratios for known contributors. From this, the analyst could make an assessment as to whether it would be worth pursuing a reference profile from a person of interest, or just seeing where the person of interest likelihood ratio sat within that distribution. We can also calculate the probability of the likelihood ratio being greater or equal to some informative threshold given those two different propositions. So this is just a simple matter of counting the number of simulated profiles that exceeded the some set threshold and dividing it by the total number of simulated profiles. So in this case, we can see the probability of a likelihood ratio greater than 1 or a log likelihood ratio greater than 0, given the individual is a known contributor, is 0.84 or 84%. And we can see that it's 19% for non-contributors. And again, I've just got these results from that program DBLR. So moving on, the likelihood ratio tells us two things. Firstly, it indicates which scenario is better supported by the findings. And secondly, it informs us of the relative degree of support the findings provide for one proposition over the other. And a verbal equivalent can help put the likelihood ratio into context for a jury who perhaps are not likely to be familiar with the scale or be comfortable with maths. So here is the recently published Swigdom scale. In this table, I've added a square bracket to mean inclusive and the round brackets to mean less than. So, for example, the first entry in the scale is a likelihood ratio from 1 up to but not including 2. And the verbal equivalent for a likelihood ratio of 1 up to but not including 2 is inconclusive or uninformative. And just as an aside, this is the only inconclusive zone that I've ever reported in casework myself. A likelihood ratio from 2 to 100 is limited support. Anything greater than 1 million is very strong support. The verbal qualifier is a qualitative statement that conveys the degree of support indicated by the likelihood ratio. Verbal qualifiers are not intended to replace the likelihood ratio, but they are intended to be a complement. And using a published verbal scale just promotes consistency with the community. So back to my single locus example, given a likelihood ratio of 14, I would report that this analysis provides limited support for the proposition that the person of interest is a contributor to the profile. So there are a number of pros for using a verbal scale beyond just consistency. For example, numbers may not be easily understood by the layperson, and research has shown that all numbers are undervalued, leading to what they call the weak evidence effect. So this is where low numbers are interpreted to support the alternate proposition. I think the most compelling reason, maybe, to report the verbal scale is that if a likelihood ratio is stated without any explanation, it's almost certain that the first question in court you're going to be asked is, what does that mean? There are alternate views, of course, though arguments against using a verbal scale would include the observation that words are subjective and arbitrary, that the numbers are fine and they don't need to be augmented with words. In one study, authors concluded that generally a greater weight of evidence was assigned to a result reported using a lower scale, and lesser weight of evidence was assigned to results reported at the higher end of the scale, so the opposite of the intended effect. I'm going to do a little experiment or a mind experiment. Let's think about what might happen if we don't report a verbal scale. So the evidence is given that the person of interest is 6 foot 3 inches. And I think we could probably all agree that someone who's 6 foot 3 is tall. And even I would agree with that. And we use the metric system in New Zealand. But what if I said the person of interest was 4.16 cubits? I don't think there would be many people that could probably comment on whether that person's tall or short. And the analogy I'm trying to make here is that the likelihood ratio is just like the qubit. Not many people outside the forensic community would understand what a given value of a likelihood ratio might mean, particularly the low values. And the verbal scale gives us a framework so we can do this consistently between analysts within one laboratory, but also analysts between laboratories. If we didn't have a scale, we would inevitably be asked what the likelihood ratio means, and at that point we might just be making something up on the spot. So here are just 3 of the many publications discussing the verbal scale and their pros and their cons. I'm referencing these 3 in particular because that's where some of my material comes from. There are scores of other published works in this area, and I encourage you to explore them if you're interested in looking at it more. I want to pick out a direct quote from one of these. It's from the 2019 paper from Heidi Aldridge, and it relates to low likelihood ratios in particular, not the verbal scale, but she stated that if you visualize reaching a verdict as a set of scales where each piece of evidence adds a stone to either the prosecution or the defense side, even a weak piece of evidence, a very small stone placed upon one side of the scale, will tip the scale ever so slightly in that direction. So I'm just going to conclude. I've got a couple of slides. What does a low likelihood ratio mean? Even a low likelihood ratio with limited support for either proposition is meaningful. And my favorite US saying is, it is what it is. And if we have confidence in our statistics through our precision, sensitivity, and specificity studies, and so long as we don't misrepresent the strength of the evidence in court, then low-level likelihood ratios are reliable to report. And I'd also like to recognise that even with modern interpretation methods, such as probabilistic genotyping, there are still some profiles that are simply too complex, and perhaps we shouldn't be interpreting them. And I'm going to suggest that's at least when you can't reliably assign the number of contributors. And we'll acknowledge that that's perhaps subjective, but we shouldn't forget that we are all experts trained in interpretation. And I'd like to finish by saying that probabilistic genotyping is a tool that shouldn't replace common sense. The burden of determining the limits of our science and the best ways to communicate our results must lie with us because we are the experts. So thank you for listening. Please feel free to reach out and send me an email if you have any questions, and pass it back to Tamara.
All right. Thank you so much, Joe. That was an excellent presentation. For the participants as well, if you have any questions for us or for Joe, don't forget that you can use that chat field to send us the questions. We might be able to answer them for you at the end of the presentations or collect them for the end of the session. For the discussion at the end. Joe, if I could ask you one question myself, I noticed at the beginning when you were comparing, I think it was a 1415 genotype to your evidence, you used the words couldn't exclude as a possible contributor. And what I've seen just in discussion with people, or as we may just speak amongst ourselves about these comparisons, we tend to use the words included, excluded, or maybe they're the situations where I can't tell. So I just was interested in your perspective about probabilistic genotyping, whether this is a system where someone is included, excluded, or if we are talking about degrees of probability and whether those terms, included and excluded, really do apply with probabilistic genotyping?
That's a good question, Tamara, and I would probably say that I haven't changed the way that I would describe a profile after introducing probabilistic genotyping. So before adopting ProbGen, we had a manual method of interpretation, but we would still apply a likelihood ratio. And I think we've always just described profiles with a bit of a descriptor before launching into the statistics. And I don't know that we've ever said included. I'm just trying to reach out back into my memory to say what I would say within a report. I'm not being very helpful, sorry.
Yeah, I'm just thinking, I think Geraldine may wish to speak up, I think our phrasing was could not be excluded as a possible contributor. I think what I'm getting at is the idea that the ways that we express things may imply to a non-scientist that we are talking about something that is absolute, someone's included.
Right, well, we certainly wouldn't say this person is included. Even if the likelihood ratio was in the millions, we would still say they could be a possible contributor, or they're not excluded, and here is the likelihood ratio or the statistics.
Very good. There you go. Okay. All right. Well, thanks for helping on that one. And thanks so much for your presentation today, Joe. With that, I would like to invite John Buckleton to begin sharing his screen and moving on to our second lecture today.
Thanks, Tamara. I hope I am actually already sharing the screen.
Yes.
Excellent. Well, welcome, everybody. I'm speaking on the subject of common court questions, and full disclosure, these have evolved with time and they continue to evolve. My experience is becoming very US oriented. I have only one European case and one UK case. I have about 46 slides and I think I'll take about 50 minutes. In the US, there are a range of issues arising, and I've put a list up here. And I just want to quickly draw people's attention to this one down here. Quite recently, I've had it suggested to me that the very fact that we're running this webinar series shows there's no general agreement on how to do probabilistic genotyping. The list of possible topics is too much for me to cover, and so I've cut it down to the ones with a little tick after them. And in many cases, I've had to tidy up the argument. The arguments presented to me in court often are not well focused and wander around a bit, and I've tried to tidy them up so that I could get them as scientifically concise as I can. I'd like to start with questions around the US President's Council of Advisors report in 2016, and somewhat strangely, I'm going to present that with the topic of code quality simultaneously. PCAST, the primary finding that intersects with us is finding 3, and they use these ponderous terms like foundational validity, which sound better than they are. But PCAST found that DNA analysis should move towards probabilistic genotyping, but they perceived that evidence had been presented in the published literature only up to the extent of 3 individuals, where the minor was 20%. Taken literally, this would mean that you can't interpret the major if the minor is under 20%, and that's clearly false. And PCAST amended their stance in their addendum so that it included the POI there. And this is symptomatic of the looseness of terminology used in this report. The reason I'm speaking about this in the connection of code quality is that it has been put out that there is no method of testing a likelihood ratio. And here is a quote: "Laboratory procedures to measure a physical quantity such as a concentration can be validated by showing that the measured concentration consistently lies within an acceptable range of error relative to the true concentration. Such validation is infeasible for software aimed at computing an LR because it has no underlying true value." And that's from Steele and Balding. This comes to me often from defense analyst Nathaniel Adams. So since it can't be shown if the system's results are correct, it is most appropriate to focus on quality assurance activities on ensuring the system's procedures are correct. And breaking that down a little bit, since you can't test the outputs, really you just need to ensure the code is correct. So if we return to the 31 Lab compilation that Joe mentioned earlier, I just want to quickly acknowledge the support of the community in helping us with this, and their names of representatives of those labs appear there.
So it looks like we might have lost Dr. Buckleton's audio. Just give us 1 second while we try to let him know so that we can get his audio back up on the line. Dr. Buckleton, it does appear like we've lost your audio. The best thing to do, if you want to try to drop out of the room and then come back in, that should reestablish your connection. All right, so he has dropped out of the room. Just give us a few moments while we work on getting his connection back up, and then we will continue on with Dr. Buckleton's presentation. It should only take just a few moments. And again, if you do have any questions for any of our presenters, feel free to go ahead and type them into the chat pod, as many of you have done, and we'll make sure to get those answered. Dr. Buckleton, can you give us an audio just to make sure we have your audio back?
All right. Let's try it this way, Josh. How's that?
That is perfect. We can hear you now, and we got cut off when you were talking about false donor testing.
Thank you. Well, maybe I'll go back one.
That's great.
Thank you. So false donor testing tests false donors against the profile. You either use a database of, for instance, staff, or simulate using population allele frequencies. Run against the profile with your system, record the results, and present. Here are the results of 28 million false donors run against that 31 lab compilation. And just to orient you, you can see on the left the different multiplexes that we used and the apparent N and known N. So we see in most cases we scored them correctly, or you can see a few where we went one under. And I'm just going to highlight this number at the top here. The highest adventitious match in this study was 500,000, and that was met with very deep consternation by an audience where I presented this. So somehow the impression has been created that adventitious matches are appalling and unexpected. And as Joe very rightly pointed out, they're neither of those. We received some criticism for our presentation of these data, but we think it would be more transparent to provide the frequency of non-contributor comparisons for all the 28 million rather than just the top 20. So I'm going to do that in a minute to satisfy that suggestion. But I'm going to be drawing on work, and I just want to acknowledge my collaborators, Duncan Taylor and Ian Evatt. And we're going to reprise Alan Turing's work again, who Joe introduced. Joe had an elegant head and shoulder photo of him, but he was also a long distance runner, so here he is, running a long distance. And as Joe mentioned, he was pivotal in breaking the Enigma code, which is thought to have shortened the Second World War by perhaps a year. And here is one of the Enigma machines that did the coding. He taught us that the expected factor for a wrong hypothesis in virtue of any experiment is 1, which translated means the average LR for the false donor test should be 1. Working with this, we can translate the verbal scale into what would be expected. So the range 1 to 2 would be expected to occur less than 1 and 2 of the time, and so on. Here are the actual occurrences in those brackets, and we can see that Turing's rule is working. So 1 in 156 is definitely less than 1 in 2, and 1 in 312 is less than 1 in 99, and so on. We see that in all cases, the rate of adventitious matches is less than expected. So I would suggest there is no cause for catastrophization of adventitious matches. They're expected, and they are coming at less than the expected rate. The less than, as Joe mentioned, almost certainly arises from the programmed-in conservativeness. A very valuable paper was published by Ramos and Gonzalez Rodrigo, and they introduced the concept of calibration. And can I just draw your attention to the title of this paper, Reliable Support, Measuring Calibration of Likelihood Ratios. And I missed this paper when it came out. If you look up the top, it's 2013. I missed it. That title is pretty eye-catching, and in terms of validating software, if someone said they could measure and calibrate likelihood ratios and give you reliable support, that should have caught my eye. I was brought to this paper by Ian Evatt, so he directed me at this, and I have met Daniel Ramos, and he's clearly gifted. What he's teaching us to do is how to measure the accuracy of likelihood ratios, and we introduce it using a weatherman analogy. So here's a weatherman, and he's saying there's a 50% chance of rain. How could we check? Well, we couldn't check one instance. If he says 50%, then tomorrow it either will rain or it won't, and in either case he's correct. But if we collected up all the times that he said 50% and we'd see if 50% of these had rain, then we'd know he's acting reasonably sensibly. So how do we actually do this? Well, in the 31 lab compilation, there are 10,000 true donors and 28 million false donors. So we can turn those into the prior odds. Each one of those has a likelihood ratio. So the posterior odds are the likelihood ratio times the prior odds, and the posterior probability are the posterior odds over the odds plus 1. Here are the results of that study. So we see in the top category there from 0.977 to 1, there were 4 false donors in that category and 7,000 true donors. So doing a little bit of arithmetic, the chance of a person in that category being a true donor is 0.9995, which we see does fall in the required category. The next bit of arithmetic turns into 0.98, and we see that that's off the top of the category. So translating that, there are not enough false donors in this category. In fact, the system is overperforming in as much as the fraction of true donors is higher than it should be in this category. We are right too often. There are not enough false donors up here. And if you fill out the list, I've bolded the ones where we're off the top. So we see here that not only is the likelihood ratio measurable and calibratable, but again, we appear to be overachieving in as much as there are fewer false donors up in this high area than expected. And again, that's almost certainly the pre-programmed conservativeness. So just bring back that this paper was 2013 and I missed it. So I certainly can't blame Mr. Adams for missing it. But here's a statement of his. Since it can't be shown if the system's results are correct, it's most appropriate to focus quality assurance activities. So I'm going to now say, well, maybe it can be shown if the system's results are correct. This calibration method, I think, does allow us to do that. Changing the topic now to one of my most hated questions, what about relatives? I've never known what to do with a question that starts with what about. So, I mean, obviously you could talk in many directions on this, so I've tried to focus the question. Does the presence of relatives in a mixture cause any negative effects? The answer to the focused question is yes, but it can be managed. So again, just want to acknowledge my collaborators. I've only got one picture to show you this time. This is Meng Lin. The rest you'll have to read as their names, please. And to set the scene here, I'll ask you to consider the picture at top left, which is a 10 to 10 to 10 mixture of a mother, father, and child. And I've used a little color code to sort of show the contribution of each person. As you can see, this will present only 4 alleles, and that's what a mother, father, child will always do. And if I get you now, please, to look to the top right, there is an equally sensible solution, which is that you have one person who's the middle two, and then another person who's the orange, and then you just use the third contributor to fill in any little bits you need. And this would come out as a 2-to-1 mixture. The 2 would be the genotype of the child, but the 1 would be neither the mother nor the father. It's a little bit of each. And it's the top right solution that StarMix finds unaided. One way to aid it and solve the problem is to condition on a parent. So in this case, condition on the father. And so we've put the father back in as grey bars. And what that now does is it locks them in there, and you can no longer get that 2-to-1 solution. It's very helpful to use the MX priors, so to lock him in at his correct amount to stop him wandering from there. If you do this, you do appear to manage the situation. It's written up here as if it's the father, but it works perfectly well with either parent, but not the child. Conditioning on the child is no help at all. Here are some results. So these are the no conditioning results. And I've made the big LRs green. And these are all the true donors, so we would expect this whole thing to be green. And we see that large blocks of it are not. And if we go up the top, let's look at the 10-10-10 row. We see that, yes, we've included the child, and we know that's because he's puffed up to suck up the bits of his parents. And neither the father nor the mother fit particularly well now, because the second contributor has one of the father and one of the mother's alleles. And if you look over on the right at the mixture proportions, you can see that, yes, we've nearly come out as the 2-to-1 false solution. As you take the amount of the child down, we do restore ourselves back to operating properly. It's that large amount of the child, especially with the mother and father equal, that causes the problem. Now, you can largely solve the problem by conditioning on one parent and using MX priors. So here we have the same format as before, conditioned on a parent with the priors. We see that the table is now nearly all green, and that's correct, except for a little patch up the top where the child is really there in a very small amount anyhow, and perhaps we'll forgive ourselves for having a bit of trouble finding a child of that low level. The sends and spec plot for that, yes, you could be concerned that you might get a sudden huge number of adventitious matches by looking at a mixture of relatives, and the answer, of course, is no, you don't. In fact, this sends and spec plot looks pretty much like all the others we've ever looked at. Little innovation that Joe and I have come up with recently is we've learned how to make the dots bigger or smaller depending on how many there are. So you can see that there's big dots down the bottom there, and that is where all the data is. So the false donors largely excluded from these mixtures as expected, couple creeping just up above the line like they do. Moving now to use of the likelihood ratio. This is thoroughly prevalent in court, and the arguments have different forms. I'm going to speak to Lund and Eyer's argument and Alan Jameson's argument. So Lund and Eyer are two friends of mine working at NIST. They're gifted mathematicians, and they have brought out that you cannot have different people assigning the LR and the prior odds. That's their point one. Point two, you should include uncertainty in the LR, maybe a distribution of plausible LRs. And Alan Jameson would argue, no one understands the LR, hence it is too risky to use in court, and further, the verbal scale is not fit for purpose. So picking up Lund and Eyer's argument, you cannot have different people assigning the LR and the posterior odds. You cannot have posterior odds of the decision maker do not equal the LR of the expert times the prior odds of the decision maker. That's probably a slightly pedantic and academic comment, but they're probably correct. But equally, I know I've never imposed my LR on a court, and I wouldn't believe that any of you guys have either. What we try to do is convey our LR to the decision maker. So I've put there LR expert and then an arrow to LR of decision maker. We try and convey it to them, and hopefully with all the good bits and bad bits explained. So this comes down to communication again. Are we transferring our LR and all the good bits and bad bits to the decision makers? Very good review paper came out by Heidi Eldridge, and Joe extracted some bits of it, and I'm going to extract a few more. It's on juror comprehension of forensic expert testimony. And she argues that because the expert is far better equipped than the layperson to opine on any strength of evidence, a reasonable approach might be to present the personal LR of the expert, but couched in terms that explicitly state the assumptions and reasoning that went into their selection of the LR that is being presented. This transparency allows jurors to both understand why the expert believes in the presented LR and adjust the strength of evidence up or down in their own minds. Now, I thoroughly support that statement. My own experience is I'm not sure how often the jurors have fully understood me, but let's go with it. I think this is certainly the high road and where we should aim. I now wish to talk a little bit about uncertainty in the LR, and you recall that one of London I's arguments are that you should express the range of possible outcomes that could happen. And I'm going to make up a little game here to try and show what they're talking about. So we have a New Zealand $1 coin, and we're going to flip it, and we believe it's going to come down heads half the time and tails half the time. And the head for us is the queen, and the tail in this case is our national bird, the kiwi. If we get a head, we're then going to roll a 12-sided dice, and we die, and we think it's going to come up a sixth, 1/12 of the time. But if we get the tail, we're going to roll a 6-sided die, and it will come up 1/6 of the time. And I ask you, what is the probability of getting a 6? So one answer is that it's somewhere between 1/6 and 1/12. And that would be the London Eye answer. You could say, well, if this, then I get a 12th. If this, I get a 6th. But another answer is just to multiply those up. So half the time we get a 12th, half the time we get a 6th. And it turns out that's actually 3 out of 24, which you might notice is exactly between those two results. Now, a sensible probabilist would do that. They would do this. It's in this case, we're summing across the uncertainties. In Prob Gen parlance, we would integrate out the uncertainty. So if, maybe this parameter could be this high, this would happen, and we would integrate it out, rather than just simply giving a large range of potential options. Now, moving forward now to no one understands the LR, hence it's too risky to use in court, and the verbal scale is not fit for purpose. I want to acknowledge that I think this is one of the challenges to the change to PG. But PG is so much more powerful at differentiating true from false donors. We just must refine our ways. Some of this argument is coming from Alan Jameson, and he points to his own paper, Perception Problems of the Verbal Scale. He ran a number of experiments, he and his collaborators ran a number of experiments where they gave to mock jurors written statements, and they had the verbal scale equivalents on the x-axis there, and then they measured the participants' perception of it on the y, and they've done this for fibres, glass, paint and footwear. And I'm going to try and take those red dots out because they distract my eye. But as you can see, I've not quite succeeded in getting rid of them. All I've managed to do is fade them out a bit. But this is the data without, or as nearly without the red dots as I can manage. The data really is meant to go from the lower left corner to the top right, and we could be a little bit hard pressed to say it does that. It's an unpleasant scatter of plots. Now, there are a number of technical faults in this experiment, but broadly speaking, probably accept their argument that this is a pretty big scatter of results. But I just want to come back to wrong by times understood is still wrong. So if we abandon PG and use some other system that people understand, it's still wrong. Right times partially understood is at the very least partially right. Now you might argue I'm lowering my expectations a little here, and maybe I am, but for me, we've got to try and get it right. Right, and at least as having really good differentiation between true and false donors. I don't want to throw all that away simply to get something that is trivial to understand. Also, I've been thinking a little bit about this. If you'd grown up and never heard about earthquakes and someone walked in and said, oh, that's a 7 on the Richter scale, you would have no idea what they're talking about. But we all do know what it is. 7 is a pretty big earthquake, and we know that because we've got quite a lot of experience of seeing news channels about, 7s and so on, and we know a 5 you can sort of feel, but probably the buildings won't fall over. So we've tuned ourselves to know what the Richter scale means. Well, I'm hoping that if we just immerse ourselves in the court experience, or we'll be immersed without even having to volunteer, and we do study and improve our experience, we'll just improve our methods of explaining these things. So just bringing back to this paper, I just want to commend it to everyone. I think she says a number of very good things. Jurors do not, as a rule, interpret forensic findings in the way examiners intend them. They often undervalue evidence, particularly if it is in a discipline that they may have previously considered to be less discriminating. They do not understand numerical testimony well, although they may prefer to hear it. And they vary widely in their interpretation of verbal expressions, although they do tend to rank them in approximately the correct order. So broad brush, they don't get it right, but at least when they get it wrong, they do tend to go under the mark. So possibly not quite as bad a problem as we might have been led. It's another layer of conservatism. One verbal cue that they seem to agree on is the term match is extremely strong, in contrast to how it is typically perceived by the forensic community. And I think Tamara may have been alluding to this in her question earlier, because we are being counselled to avoid match. Basically, the jury think we're saying it's him. So Tamara didn't use match. She talked about inclusion and exclusion. We may have to change away from those words. And I guess the topic's open, but at least we could possibly go to inclusionary and exclusionary. I want to end with my aeroplane analogy. It's not worked out all that well over time, but giving it another go. So here is the Great Circle route from San Francisco to London, and you'd go up across Canada and Hudson Bay and then Greenland and then come down again. And I ask you, which of these would you like to go in? Do you want to go in the Wright brothers machine there, or this beautiful Air New Zealand aircraft? And just for the record, Air New Zealand is in the top 20 airlines by safety. They won't tell you where in the top 20 they are. They just say these are the top 20.
So what would you take? Well, I'm going to go on that thing, the Air New Zealand one. But I guess the question is why? So here's a quote I've recently had. Someone took my airplane analogy and turned it back on me in court. No one wants to be in an aeroplane where only some of the software meets IEEE standards, even if the alternative is a plane with even less of the software, where even less of the software is consistent with those standards. So that's what was said. I still want to go on the Air New Zealand plane. And I want to end this analogy with, we just cannot afford to throw away our best tools. PG is the best tool for differentiating true from false donors. We just have to get better at using it and presenting it. So a few little conclusions. Adventitious matches can and always could happen. This isn't new. They're happening at less than the expected rate. The absolute value of the LR can be tested by calibration, and acknowledgements to Ramos and Rodrigo Gonzalez for their gifted work. Mixtures of relatives can cause problems, but there are management strategies. Communicating statistical evidence is and always has been challenging, and the answer is to improve communication, not throw away the evidence. And with those words, I'll turn us back over to Tamara.
That's great. Thank you so much, John. We're going to take a break in a moment, but I'd like to throw maybe a tough question at you, John. This is my own question, getting back at one of your earlier slides. The question about whether the webinar here shows that there is no general acceptance. So what are your thoughts on that particular issue?
Well, Tamara, thanks for that. I mean, I gave my thoughts in court, and I'm happy to give them again now. And I was very grateful to have been involved with you in the development early on of this course and the conceptualization of it. So I actually know the answer, of course, which is that we're just, this is ongoing continuing education. This is part of the maturity of the community. This is how you do things. This is, the existence of standards and controls and education are what really we should be doing.
Very good. I couldn't agree more. That was the intent. I know so many labs are in the process of choosing softwares and learning about them and the systems and approaching their validations and then having to decide what to do, developing standard operating procedures. So we're here trying to get as much information out from all of the experts as we could pull together in this format. So thanks for that, John. Thanks so much for your presentation today. We've got a few questions. Perhaps what we'll do is take our break now, give all our speakers a chance to review the questions, and then before we jump into our next presentations, we'll come back after the break and address those questions. So let's return. It's 1:21 now. Let's return at 1:30 Eastern Time. Thanks so much. Okay, welcome back everyone. We're ready to start up again, and let's begin by looking at the questions that we have gotten so far. Unfortunately, Joe Bright had to return to the course that she's teaching this week, but we have all of our other presenters and speakers here with us today. So I am going to share my screen so that we can see the questions. Here we go. And we had essentially 3 questions so far in the series. So I'll read the first one. If the expected value, LR value, is 1 for a non-contributor, how can this be explained to a jury? Would anyone like to take that question to answer it?
So I guess I said it, Tamara, so I'll have a go. I have never said that to a jury. What that is it's part of the way that you move towards working out that the chance of an LR bigger than 100 is less than 1 in 100. So it's sort of an intermediate on that way. I don't know how I'd explain that in court.
Okay, I think as well that I'm reading through the comment on that question, and I think that has to do with a different issue, which is when you actually get an LR of 1, and that's explaining how we describe an LR of 1. John, can you tell us, say how you would describe to a jury what it is an LR of 1 means?
Well, a one has to be about the easiest thing to describe, I would have thought. It's just uninformative. This evidence does not differentiate between the propositions at all. I think the fun comes in when you're talking about an LR of 10.
Yeah. Okay. Hey, Geraldine Conway is on the phone as well from the FBI laboratory. Geraldine, can you speak to what the FBI does regarding the next question, which is, does anyone include a statement in their report when a low LR is obtained? And I think because of a very partial profile, and I think that is referring to adventitious support rather than true low support when the person of interest is a true contributor. I think that's what the question is asking. You might not have Geraldine unmuted here on the conversation. We might come back to that at a different point unless anyone else wants to speak up on the question. And then the last one is, when using a verbal scale to a new audience, such as a jury, how important do you think it is to stress that it's a two-sided scale, meaning that support could apply to H1 or H2, and to provide the full scale? I seem to recall the Jameson paper specifically did not provide participants with the scale, just a single entry.
So, Tamara, I think it is important to provide the full scale, and I think that helps ensure that people at least understand that's an ordering, and I think, yes, we should show it's two-sided. I think that's enormously helpful.
Okay, do you recall whether the Jameson paper and their views, whether
Yes,
they had informed?
Yes, I believe that's true. I have the paper, I'll check quickly. But there are also a number of other technical experimental design issues with the paper. So it's possibly not the finest piece of work on this subject.
Okay, all right. Well, thanks for bringing that to our attention as well. Okay, with that, I would like to move on to our next speaker and introduce Ted Hunt. Welcome, Ted. Thanks for joining us today. And feel free to start sharing your screen when you're ready.
Ted, it looks like you might be muted. We're not able to hear your audio right now.
Okay, I'm here. Can you see
There
my
you are.
presentation?
We can see your screen. So if you just want to bring up your PowerPoint. There you are. And then just start your slideshow and then hide your Blue Jeans is sharing your screen message. Perfect. You are good to go.
All right, great. Thank you very much. First of all, I want to recognize Tamra and the FBI Laboratories DNA Support Unit and Josh Vickers and our partners at RTI for putting on an excellent series. I've watched a number of them thus far, and they have been truly outstanding. So thanks to all of you. Also want to thank Doctors Bright and Buckleton before me, and good afternoon and morning, I guess, or evening, depending on your time zone. We're going to switch focus a bit here from probabilistic genotyping to the role of the expert in the American judicial system. And my talk is entitled The Role of the Expert because there aren't special rules that just apply to DNA analysts and no one else. And the reason that I want to talk about this today is in the forensic literature in the last number of years, lots of statements have been made about the role of the court and the role of the expert. And those statements aren't specific to any judicial system. They're pretty much general statements that have been pushed out in the literature. So we thought we'd take a deeper dive and look at the American judicial system and the role of the expert in it. And my approach is going to be to talk about those rules and then to transition into a legal review of likelihood ratios in U.S. courts to date. My focus is going to be descriptive in nature. I'm going to try to describe what the rules are, and I'm going to try to minimize any focus on being normative or talk about the way things should be. I'm also going to try to use a visual approach so that we don't get too bogged down in legal jargon and you can kind of see the flow of information that I'm trying to convey as I'm doing it. So the first question is one of motivation. Who cares? Why should you care if you're a state or local DNA analyst and you're listening to this talk? Well, the motivation is here in front of you. This is a map of the U.S. and all of the states in red have adopted the federal rules of evidence or some version of them. So the legal rules that I'm going to be talking about that are more or less specific in large part to the federal system actually have great applicability to state and local jurisdictions, if not completely for the most part. So I think the things I'm going to say are going to be general truths that are transferable to your jurisdiction. First of all, I want to talk about the concept of the admission, the exclusion, or the suppression of expert testimony. And as I said, I'm going to try to be visual with this. A lot of times the distinctions between different types of admissibility are sort of glossed over and it can cause some confusion. So if you look at the left of your screen, we've got what is most often discussed in the community, which has to do with admissibility motions. These are motions to exclude or admit evidence. And the standards, which you may have heard of from time to time, are the Frye standard and the Daubert or Kumho-Tyre standard. One party or another, it can be the defendant or it can be the prosecution, can challenge the admission of scientific, technical, or specialized evidence in courts of law. And typically, although not exclusively, there's a pretrial hearing. These can also happen during trial, and a judge can decide to entertain motion at that time. After that motion has been heard, the judge either admits or excludes the evidence, and as the saying goes, if justice prevails, you can always appeal. So there is a chance for appeal by the defense post-conviction. if evidence is excluded that the government offers, it can appeal through this statutory mechanism before trial. And if evidence is admitted on the part of the prosecution and the defense wants to make issue of that during trial, they can later appeal on those points raised during that trial. When you move to the right on the chart, you've got your typical evidentiary objections. And if you've ever been a witness at trial, you may have heard one of the parties say objection. Parties approach the bench. They try to whisper to the judge. Often, in my experience, you can, as a juror, clearly hear what we're saying at the bench because you hear them chuckle. Some courts have even gone to some type of a white noise device to prevent that discussion from being overheard. But nevertheless, these are objections that are raised during trial in real time during examinations. And if the judge overrules the objection, the evidence is admitted. The defense is grieved by that. They can appeal post-trial. During the trial, if the evidence is excluded, that means that the objection was sustained, and the defense can appeal post-trial if they're on the receiving end of that adverse ruling. Over to the right-hand side of the screen is a separate type of motion, a motion to suppress, which lists some constitutional grounds, typically the 4th, 5th, or 6th Amendments to the Constitution, as reasons that the evidence being offered by the expert should be suppressed. And suppression has to do with constitutional issues. Exclusion has to do with evidentiary issues. Again, these can be raised pre-trial or during trial in the discretion of the court. If evidence is admitted, the defense has a chance to appeal if they're aggrieved by that admission. And if the evidence is suppressed, the government can appeal pre-trial by statute. So that's kind of a breakdown of the different types of admissibility when we're talking about. On the left-hand side, typically it's before trial. In the middle, during trial. On the right-hand side, it's before, during, typically before trial. But there's a different legal basis for that. You all may have heard, probably should have heard by now, that admissibility in terms of scientific evidence got its most famous start in 1923 with the D.C. Circuit Court of Appeals in the Fry decision. And a very short decision, and the operative paragraph from the opinion is the one quoted here. Just when scientific principle crosses that line between experimental and demonstrable is difficult to define. Somewhere in the twilight zone, the evidential force must be recognized, and the thing from which the deduction is made must be sufficiently established to have gained. There are the words you've heard, no doubt, general acceptance in the particular field in which it belongs. So the advent of the term general acceptance comes from the Fry case. Fast forward to 1975, and the federal rules of evidence are enacted by Congress, and 70 years later, in the Daubert case, Daubert versus Merrill Dow Pharmaceuticals, the question for the Supreme Court was, did the federal rules of evidence incorporate the Fry standard or not? And as you know, the Fry standard is the general acceptance test in the relevant scientific community. And the answer was that the Fry test was superseded by the adoption of the federal rules of evidence. And Daubert is a much quoted, much cited, much discussed case. And exactly what that means is being litigated, no doubt, in courts in the United States this very afternoon, when certain litigants are trying to admit or exclude facts that it may or may not come into evidence. So to break down Daubert a bit, Daubert deals with scientific knowledge, and we'll get to the other types of knowledge that federal courts wrestle with in terms of admissibility here in a moment. But the first question the court has to determine when you're dealing with scientific knowledge is, one, is it scientific? And two, is it knowledge? And the Daubert court actually breaks these concepts down and describe scientific as something that's grounded in the methods and procedures of science. And knowledge is any body of known facts or ideas inferred from those facts and accepted as truths, asterisk, on good grounds. And the reason there's an asterisk there, the court recognized that there are no absolute truths in science, but in a sense, we're talking about contingent truths, those truths that are based on good grounds at the moment. So again, Daubert tried to define scientific knowledge, and the legal equivalent of that, according to the court, on the legal side, is evidentiary reliability. And reliability in the law is quite different than it is in science. Science reliability is typically something like consistency. In the law, it is trustworthiness. And scientific knowledge is, according to the court, something derived by the scientific method and supported by appropriate validation. And Dr. Buckleton just got finished discussing the PCAST report and the terminology used in that report. PCAST report took the concept of validation and broke it into two parts. Created, as far as I understand, the term foundational validity. Hard to find that anywhere before PCAST, and then they also proposed a term, validity as applied, and had to do with the application of the foundational technique in the particular case at hand. And again, good grounds is basically the standard for appropriate validation based on what is known. Again, the contingent nature of knowledge based on what we currently know is reliable. So to break Daubert down a little bit further, as you may have heard, the judge's role in the process is the gatekeeper. And Daubert set forth that responsibility to the judge and to the judge alone. In general acceptance standard, the judge typically looked to see what the community thought and sort of accepted that verdict, if you will. The change from Frye to Daubert is the judge independently has to make that determination of reliability aside from what the community itself might think. That was the basic sea change from Frye to Daubert. And again, the question is what is in front of the court? Scientific knowledge. And that has to do with reliability and relevance. Low reliability box, the judge also has to determine whether the evidence is relevant, and what that means is, will this information, this data provided by the expert help the jury understand the evidence, or alternatively or cooperatively help them determine a fact and issue? And that assessment led the court to offer what they called some general observations. Those general observations have been nearly universally termed as the Daubert factors, although the court was quick to say this is not a checklist. This is a preliminary assessment about the reasoning and the methodology to determine whether it is scientifically valid and properly applied. And the questions were, the observations that the court put forth for trial judges to consider were, can or has the method been tested? Has it been subject to peer review and publication? Is there a known or potential rate of error? And are there standards that have been maintained that control the technique's observation? And for good measure, the court threw in general acceptance as well, because that can tend to provide some kind of information about the reliability and perhaps the relevance of the method at issue. The court was quick to say this inquiry is flexible, and it has to be when you're dealing with case-specific scenarios. Again, evidentiary reliability is trustworthiness in the law, and we make sure that trustworthiness and scientific knowledge are coterminous here. And the overarching inquiry is the validity of the technique or the method, again, based on good grounds. Evidentiary relevance has a couple components. One, will the evidence assist the trier of fact? The court described that as helpfulness to the jury. And secondly, is there fit? And this has to do with the connectivity of the issue to the evidence. And I like to think of electrical outlet and a plug. There has to be that connection. And I also like to think of the probative value as sort of the volume on the dial. If it's anything less than minimal legally, it is typically relevant. So a few years later, 6 years after Daubert came along, another case, Kumho-Tyre, a less well-known case in the scientific realm, but nevertheless very important for our purposes as well. And in this case, technical or specialized knowledge rather than scientific knowledge was at issue. And the judicial gatekeeping role still applies in this context. But there's a slightly different analysis here. The trial court may but need not apply the Daubert reliability factors depending on the method or the technique at issue. But still there has to be a reliability assessment, although the court was quick to add that has to be flexible. And the court has broad discretion to determine a few issues: how to determine reliability, whether the evidence is reliable, and whether there's even a need for a hearing. So this is all within the discretion of the trial court to determine. The court also described the differences that may be at hand between this and strictly scientific evidence. In many cases, an expert that operates in this realm is dealing with observations that are then assessed through technical or specialized knowledge or experience, and the case at hand is a very important aspect to this analysis. There still has to be a valid connection to the pertinent inquiry. The relevance has to exist, and the reliability does as well. But the use of the Daubert factors, the court advised, are only when those are reasonable measures of reliability. So that depends on the particular facts and the task at hand. The third case in the trilogy, and actually this was the second one in order, was General Electric versus Joyner from '97. And in this case, the court determined what the trial court's gatekeeping decision was to be in terms of what standard should be applied, and the court found that the appropriate federal appellate standard was abuse of discretion. Another important aspect of the case, however, was what's essentially some dicta that had to do with the methodology and the data utilized. Anytime you have a method and you apply that to data to get conclusions, you're going to have some extrapolation. And the court made it clear in the Joyner case there has to be a fit or a nexus between the methodology and the data and those conclusions. And that extrapolation can't result in an analytical gap that is too great between the method, the data, and those conclusions. And the famous phrase from Joyner is the expert's opinion must be more than ipse dixit or an unsupported statement. Just because he said it doesn't make it admissible. You've got to show the roadmap, if you will, from the method and the data to that conclusion. There has to be that nexus there that the court can follow. After the Daubert trilogy, Daubert, Joyner, and Kumho-Tyre, in 2000, Federal Rules of Evidence 702 and 703 were amended to incorporate the court's, wisdom or extrapolation from those cases to embed them into the rules. So that happened in 2000. The rules were amended in 2011 for style only. So we're going to look at a few more rules, and we'll get into some case examples here in a moment and see how this ties together. Federal Rule of Evidence 104 has to do with the judicial gatekeeping role. As you can see, the judge is the gatekeeper. Here's where you can actually find that. The court must decide these preliminary questions about the admissibility of evidence and qualifications. And the standard the court has to follow is a preponderance of the proof. It basically means more likely than not. That's derived from case law. And the evidence has to be relevant, but many times relevance is conditioned upon fact. And when that's the case, the relevance of the evidence depends on the existence of that fact, and proof has to be introduced sufficiently to support a finding that that fact does exist. And the court may admit evidence in its discretion before that proof has been introduced on the proffer of one of the parties that will later come in. And if it's not tied together later, then the expert or the party always runs the risk that that testimony will be stricken because it's not conditionally relevant. The basic rule of evidence dealing with relevance is 401. Relevance is not something inherent of the evidence. It has to be conditioned as a relationship between evidence and an issue, a proposition, or a fact. And the standard, as I said a moment ago, is very low. If evidence has any tendency to make a fact, or you can insert a proposition in there just as easily, more or less probable than it would be without the evidence, and that's step one. Step two is the fact or the proposition must be of consequence in determining the action. So if you think in terms of this analogy between an outlet and a volume knob, the volume knob for probative value is paragraph A, any tendency. Paragraph B has to do with the fact or the proposition of consequence, and you could think of those in terms of a prosecutor's hypothesis or a defense hypothesis. And you could think of, here we have an LR scale that is from the department's uniform language for testimony and reports. If the evidence has any tendency to make fact or proposition more or less probable, then it is admissible. And the tendency just means simply that. If there is a tendency, it is admitted. Very low bar. So we've got a relevance conditioned on fact, a minimum threshold, a conditional relationship between the issue or the fact and the evidence. And according to the comment of the rule, that's assessed using experience or science logically applied. And we talked about the fit that's necessary. You may have heard of the term legal foundation. Brick does not make a wall. Building blocks of relevant are discrete facts. And here we have an example of 6 discrete facts. Or in your experience, maybe questions in court and answers to those questions that lay a foundation, as we call it, for that evidence to be admissible. So many times evidence is conditioned on facts coming in that support their relevance, and many times it takes a number of questions to establish competence and qualifications of an expert, to establish a chain of custody, what we call authenticating the evidence, and then thirdly, information, data, or a method to support an expert opinion takes a number of facts that we need to build as if facts were bricks in a wall to get to the point where that evidence is relevant or reliable. Now, having said all that, Federal Rule of Evidence 403 actually trumps 401. So if you have relevant evidence, it could actually be excluded if its probative value is substantially outweighed by one of these factors: unfair prejudice, confusion of the issues, misleading, undue delay, waste of time, or cumulative. That's in the trial judge's discretion, and the judge has to balance the probative value against the prejudicial impact. And if the probative value is substantially outweighed, even though the evidence is relevant, it can be excluded. Now, jumping forward to Rule 702, This is the primary rule about the admission of expert testimony in the federal system. And a number of parts to it outlined on the right-hand side. A witness who is qualified as an expert by any one of these factors, knowledge, skill, experience, training, or education, may testify. And that has to do with what we call in the law competence to testify. You're qualified to testify as an expert. Legally, you're competent to testify. If in the judge's determination, remember Rule 104, you meet a minimum level of criteria to qualify as an expert. And the form of the opinion can be opinion or otherwise, and we'll get to what otherwise means here in a moment. The expert's scientific, technical, or other specialized knowledge has to help the trier of fact, understand the evidence, or determine a fact and issue. So these are the requisite types of knowledge. There's a relevancy requirement, and this has to be something that's beyond the knowledge or the experience of the finder of fact. Stated simply, this is beyond the ken of the average juror, so it's not something the jurors can figure out for themselves, or they wouldn't need an expert. So this has to be something that goes beyond that threshold, again, in the determination of the trial judge. Testimony has to be based on sufficient facts or data. That's a quantitative component. Minimum threshold has to be sufficient. The testimony has to be the product of reliable principles and methods, the reliability requirement of the underlying methods. But there also has to be reliable case-specific application, and this is the fit to that testimony to the case and the task at hand. There has to be that connection or nexus to this particular case. And if all of those criteria are satisfied, again, by a preponderance of the evidence, then the court will admit the testimony. If not, it can be excluded. Now, the advisory committee understood that experts can look at the same picture, if you will, and come to different conclusions. Think about a portrait or a piece of art. Somebody will look at it and think it's the greatest thing they've ever seen. Some will pass by without hardly giving it a second look. And the committee understood that when facts are in dispute, no surprise, experts sometimes reach different conclusions based on competing versions of those same facts. But the court's emphasis is to be not who's right or wrong, or whether the court believes one version or the other. Rather, it's whether those facts are sufficient. Well, what qualifies one as an expert? We looked at this preliminary question of fact for the court is one of legal competence and qualification, and any one of these criteria alone or in conjunction with others can do the trick. It can be knowledge, or in something that is less scientific and more technical or specialized in nature. It can be skill, experience, training, or education. But I should hasten to add that even in the purely scientific realm, sometimes experts testify from experience, training, and education, and skill. So these are not mutually exclusive to different types of knowledge. An expert possessing one or more of these, depending upon the scenario, can be properly qualified to opine in the case before them. So back to form. The form that the testimony must take is either opinion or otherwise. An opinion is relatively straightforward. Well, what does otherwise mean? And I think if you look at these different descriptors, they pretty much reflect what's in the case law. An expert need not opine, but their testimony is still admissible if they're providing basis or background facts or data. They're simply explaining or describing something to the jury. They're educating the jury, or they're even summarizing their testimony or the testimony of other witnesses foundational to their own. So an expert could come to court and not provide an opinion at all. their evidence would still be admissible, and all of this is subject to Rule 702 and the other applicable rules of evidence. Another important rule to be aware of, and like I say, these are federal rules of evidence, but if you look in your state, it's probably in your evidence code as well. Federal Rule of Evidence 703 talks about the fact that an expert can base their opinion on a number of things: learned facts or knowledge, facts or data in the case before the expert, facts that the expert has been made aware of outside of court, or facts that are hypothesized to the expert in court, and we'll get to that in a moment. The threshold here has to do with reliability in terms of a reasonable reliance on those kinds of facts or data informing an opinion on the subject in that particular field. This is more or less a qualitative, field-centric reliance test. This is not necessarily based on the judge's belief, but the judge inquires as to what is the type of information or data reasonably relied upon by experts in that field. That's kind of getting back to the old general acceptance test, where the judge doesn't make an independent determination, but determines what is typically or reasonably relied on by experts in that field. And in making that assessment, reliance on hearsay is okay. Hearsay is basically information that was heard or learned outside of court that the expert might testify to. But it's also important to remember that disclosure of that information from outside of court to the jury is balanced by a test that requires the trial court to only allow hearsay when its probative value in helping the jury evaluate that expert's opinion substantially outweighs its prejudicial effect. So that's a judicial call that has to be made. But this is the rule that allows information and evidence from your education, your training, your experience that you bring to bear, whether it be scientific literature, papers, or textbooks, things outside of court that you have to necessarily rely on as an expert, that can be used to help formulate your opinion. It's just how much of that can come into court is the question. So if we look at the different bases, we've got the facts perceived by the expert, the first-hand knowledge, and or facts presented at trial, hypothetical questions, assumed as true by the expert, or facts learned outside of court, reliable hearsay, assumed as true by the experts, and an LR proposition or set of propositions is one example of that. Something formulated outside of court, assumed as true for the purpose of the expert's testimony. Now, an expert may assume those facts, contested facts and propositions, as true, but those assumed facts and propositions must be based on facts that are in the record or will be introduced as part of the record. The expert may assume those facts or propositions, but the expert may not assert their truth without support coming in the form of admissible evidence. So the support is assumed for those facts or propositions, but that evidence must be independently admitted into the trial record. Now, in cross-examination, an expert is not forced to and need not assume facts or propositions that he or she knows to be untrue or inadequate. And there's no indication those facts are or will be later introduced at the trial. So there are some limitations on what the expert can assume, and the timing of that is all up to the court, who has discretion over the order of proof. Federal Rule of Evidence 705 states explicitly that the expert may state an opinion without first disclosing the underlying basis for those facts, and puts the onus on the cross-examining lawyer to bring out those deficiencies with those basis facts, or the underlying strength of that opinion. Think of a house of cards. If the expert's opinion is nothing but a house of cards, the responsibility is on the expert to defend that opinion in light of the cross-examination that may come. And if that is not well-grounded, well-founded, then that opinion is subject to exclusion. Now, I mentioned before at the beginning of this talk that a lot of literature has the role of the courts and the role of the expert, and this is forensic literature. I have some examples here. The European Network has its guideline for evaluative reporting in forensic science, and number 3 here in this excerpt talks about the role of the forensic practitioner to consider the probability of the findings given the propositions and not the probability of those propositions. Similarly, other documents in the community from Australia, New Zealand, from Dr. Vet, and from the Association of Forensic Science Service Providers, all basically say the same thing, talking about the role of the expert is to comment on the probability of the findings given those propositions and not the propositions themselves. This has gotten into the U.S. forensic community to a certain extent on the left as the National Commission's views document. Just want to be clear, this document did not get voted to approval through the commission, but nevertheless, there is a final standalone version to that document that basically says the same thing. Forensic practitioner should not state a specific individual or object as the source of forensic evidence, and refers to the formal method of evaluative reporting as well. And basically the same people who wrote that document wrote the American Statistical Association document, which for the most part says the same thing, discouraging the statements to the effect that a specific person or object is the source of evidence. However, in the U.S. system, there is Federal Rule of Evidence 704. And this is a rule that you don't hear much about, and I think there are some people who would like to pretend that it doesn't exist, but it actually goes against that school of thought and allows an expert to opine on an ultimate contested factual proposition before the court, not only on the strength of the evidence for or against a proposition. Specifically, an opinion is not objectionable just because it embraces an ultimate issue, and you can add proposition in there as well. I need to add that 704 does not lower the bar to admit otherwise inadmissible evidence. The rule works in conjunction with the other rules of evidence. The only exception in the American system or the U.S. federal system is that the expert may not opine on the defendant's mental state, an ultimate legal fact or proposition before the court, or witness credibility. However, they can opine on an ultimate issue. Just as an example, this is a latent fingerprints case from the Ninth Circuit in 1996, and a defendant objected that the expert was specifically testifying that he had no doubt that the prints on the piece of evidence were the defendant's. The defendant objected because the expert was testifying to an ultimate issue, and the court basically said, so what? The argument fails in light of 704, which permits an expert to opine on ultimate issues in a case. And like I said before, I'm trying to be very descriptive. I'm not being normative, and I'm not weighing in on the logic or the advisability of this. I'm simply trying to correctly state what I understand the law to be. So in the DNA context, this would allow a source attribution statement. There are 3 federal cases that I know of that have permitted source attribution in the DNA context, although I need to hasten to add that each of these cases involved random match probability, not an LR, and the issue of source attribution relative to an LR, as far as I know, hasn't come up yet. You may be familiar with some of the forensic documents that have permitted this within the forensic community, like the DAB, DNA Advisory Board might have been the first to speak on this, NRC2 in 1996, and then the SWGDAM interpretation guidelines for autosomal STR typing also permits this, subject to explaining how you got there. So there is legal authority for this opinion on an ultimate issue in American courts, despite the fact that some of the forensic literature says the role of the expert is not to do that. Again, I'm not advocating that. I'm just simply explaining that the literature may be at odds with what the law permits. Looking at this in the context of the hierarchy of propositions, an expert could opine on an ultimate issue or proposition at the subsource, source, or activity level. They could not opine, of course, on the defendant's guilt, the defendant's mental state, legal definitions or conclusions, or witness credibility. However, other than that, pretty much everything's fair game. And if you look at the quote at the bottom of the screen, this is straight from the committee's note to Rule 401 that we covered earlier. The fact to be proved may be ultimate, intermediate, or evidentiary. It matters not so long as it is of consequence in determining action. Now, in our uniform language for testimony and reports for probabilistic genotyping, specifically in the qualifications and limitations section, we do have a provision there that recognizes that we're dealing with continuous data, and we disallow an expert from asserting that a likelihood ratio of any magnitude provides an absolute identification or source attribution of a known individual to an evidentiary sample. So that is a choice that we have made that may be inconsistent with what the law actually allows. I want to give a case example, and this is not a likelihood ratio case. This is an RMP case, but I wanted to show how a case that started out as a source identification or a source attribution in the DNA language was ultimately reduced to rubble. This is a case that involved the robbery of a gas station. There were 2 suspects. Suspect 2 struggled with the employees, and they're shot during the struggle. Suspect number 2 left behind some clothing. His face was never seen, and 2 suspects were later identified as brothers. So the results and conclusions from the DNA, they're really the one you need to look at here. It's the 1 in 814 billion. And testimony offering source attribution was provided at the trial. And the trial court, after the defendant was convicted, the New Jersey Court of Appeals affirmed that on direct appeal. There was a subsequent motion alleging ineffective assistance of counsel. His counsel failed to confer with or call a defense expert. The motion was denied by the trial court. The appellate court, however, later weighed in and said that the DNA alone was the substantive evidence, tying the suspect to the crime, and the state's expert testified to this conclusive link. And because the defense counsel did not investigate the DNA evidence to find a basis for a challenge, and there was no reasonable basis for that failure, this court ruled that the RMP of 814 billion for the exterior of the hat that was left at the scene was challenged by the expert post-conviction who calculated the probability, and I can't vouch for these calculations. There's no basis for that in the opinion. But the expert post-conviction calculated the probability that the defendant would share his DNA with one of his two brothers was 1 out of 1,076. So, the court said the jurors were deprived of the evidence distinguishing between this very low probability that the DNA profile would occur in all African American males, including the defendant's brother, and the substantially greater probability of 1 out of 1,000 or so that it would match or occur in one of the defendant's brothers. So in addition to the probability that DNA may have been shared by a sibling, that was of particular relevance because one of the employees suggested the hat in which the DNA was found was not that worn by the perpetrator. In addition, and importantly, the defendant's brother, Lyle, was positively identified as being present at the crime scene. So although this isn't an LR case, it's an example of where laboratory analysts need to be aware of the facts of the case in forming their propositions. Because if it's alleged that there is a brother or another close relative involved in the crime, that could drastically impact your propositions and the ultimate statistics that are testified to in the form of an RMP or an LR, what have you. So it's important to keep in mind that we cannot operate in the dark away from the facts, whether they're filtered through an independent source inside the laboratory or whatnot. They need to be informed by what the balance of the case facts are. So we talk about that background information is so important in formulating the LR for a number of reasons, especially since an LR is basically the answer to a specific question that's asked. Maybe there's more than one question that's important in the case. Analysts and counsel, whether they be prosecutors or defense, need to be in contact with each other. Make sure that relevant propositions are put forth in the case instead of just supposing the negation of the prosecutor's hypothesis or H1. Experience-based testimony in scientific issues. This is a topic that I want to cover. This is a fairly influential case, Frazier from the 11th Circuit in 2004. It's a kidnapping, sex assault case. And quickly, the proposed testimony by a defense expert here had to do with the absence of expected evidence. None of the suspect's hairs or body fluid were recovered from the victim, her clothes, or her car. And the defense expert, pre-trial, opined that it would be expected that some transfer would occur. He also opined there was no forensic evidence to substantiate the claim of rape in that case. This was a fairly experienced expert, had been a police officer for many years, was employed at the time of trial as a forensic consultant, had done 150 to 200 cases, had worked in a medical examiner's office, had received training, had FBI crime lab processing experience, undergone criminalistic studies, taught classes, and qualified as an expert. So someone who's typically going to be qualified as an expert. But there were some limitations to the claims. He opined that hair was the most common form of evidence in rape investigations, and he'd expect some transfer of either hair or seminal fluid if the offense had occurred. His opinions, however, were based on experience and two-sided textbooks, but when it came right down to it, his case-related experience wasn't all that great when it came to the fundamental question, which was the number of cases he personally worked on that involved transfer of hair or seminal fluid. And he didn't cite any specific scientific literature on the rate of transfer of hair in sex assault cases, and only offered some texts that were not actually offered or admitted into evidence. And he merely cited his general experience and the text as foundation for his claim about frequency of transfer. So the court permitted some testimony. The investigation was proper and thorough. He opined but there was something missing. He would have expected to see some kind of transfer. So he had these things on the left side of the screen. To his credit, the judge allowed him to testify to those, but on the right-hand side, this information was excluded. Based on the facts described by the victim, it would be expected that some transfer or some kind of evidence would have been left behind. That wasn't allowed. Forensic evidence did not substantiate the allegation of rape. That wasn't allowed. And there was no forensic evidence to substantiate that at all, stated a little bit differently by the court from point 2. The Court of Appeals ruled that the district court did not abuse its discretion in excluding the testimony. So if you follow this graphic, the hair and semen would be expected. The meaning was unclear. What would be expected meant in terms of both reliability and relevance, and these are the reasons. There was also an insufficient factual foundation. And the court added that this foundation can come from either experience or from studies or treatises. But the expectancy conclusion had a probabilistic element to it. And there was no transfer rate information offered, no reliable studies, and no quantification from experience. However, the court was quick to add that experience alone could have qualified this expert with a sufficient foundation. And that's consistent with the advisory committee's notes to 702, which specifically say that experience alone can provide a sufficient foundation for expert testimony. But those building blocks have to be put together to build that foundation for a sufficient foundation in experience for that evidence to come in. So the court ruled that exclusion of evidence was permissible. And the advisory committee note also recognizes that when someone's testifying solely based on or primarily based on experience, they have to explain how that experience leads to the conclusion, why that experience is a sufficient basis, and how that experience is reliably applied to the facts of the case. And the trial court is not to just take the expert's word for it, getting back to the Joyner opinion and its statement about ipse dixit of the expert. So I call this the how, why, and how rule. How does that experience lead to the conclusion? Why is this foundation based on experience a sufficient basis for offering that conclusion? And how does that experience lead to a relevant and reliable conclusion applied to the facts at hand? So when you look at this, we've got the Joyner case here about the analytical gap. We've got the basis requirements in 702 and 703 here. And then the how question, how is this conclusion reliably applied to the facts at hand, brings in Kumho-Tyre. So in U.S. courts, again, experience is sufficient, but you have to, again, base that experience on a sufficient factual foundation. However you can do that. And that's up to the trial court in that particular case on those particular facts. In terms of alternatives, explanations, causes, Dr. Buckleton testified about some in the community who currently believe that an expert's job is to offer all models, all hypotheses, all data, and let the jury sort it out. But that's not actually what the law says. An expert does, if they're challenged on cross-examination, have to adequately explain why obvious alternatives are ruled out. And obvious has been interpreted to mean something sufficiently strong, an evidentiary nexus between that alternative and the proposition, but you do not need to explain every alternative, provide all the data, or all possible propositions. Experts are entitled to make reasonable choices, and they can assume certain facts as true and disregard others. They are going to have to face a cross-examination that explores those omissions, and if those omissions are great enough, then potentially the expert's opinion can be excluded. There's no duty on the expert to ground the jury in all possible models or data and say, good luck, you figure it out. Part of the expert's role is to explain that data, to describe it, and to put it in context. And part of the litigant's role is to point out omissions in that expert's opinion. So to sum it all up here, when we talk about breadth and depth, let's look at breadth first. An opinion or otherwise, the limits are only the rules of evidence and relevant case law. And the depth of the expert's testimony on opinion is as to evidentiary facts, intermediate facts or issues, or those that are ultimate in nature. Again, the limitations are only the rules of evidence. When we talk about otherwise, other potential grounds for testimony or basis or background facts or information, explanations, descriptions to educate the jury or to summarize. Again, the only limitations are the rules of evidence and relevant case law in a particular jurisdiction. So in the last few minutes here, I want to provide a quick summary of some LR case law. I'm bypassing all of the law that has to do with admissibilities of different software systems and just trying to focus on the LR itself here real quickly. First of all, I want to make the point that in ILAC G19, LRs are implicitly included there. 4.81 talks about hypotheses that should be defined, and alternatives should also be considered. And the consideration of one or more alternatives shows an organization is demonstrating its impartiality. So that's actually built into the accreditation framework. Here are a couple cases that talk about the LR being generally accepted in the scientific community. Before ProbGen came along, there were a smattering of cases where LRs were used. I guess the genesis was probably the paternity context, criminal paternity. But there were a few isolated usages of LRs that made their way into some appellate case law. And here are a couple. One from Illinois, one from Arizona. Dr. Weir was testifying to his LR formulation that was from NRC2 quite some time ago, and the court in Arizona ruled that that formula was generally accepted in the scientific community. Another case from Montana concluded that in the Daubert context, the LR is not a novel scientific technique that warrants analysis under Daubert, so no hearing even allowed. However, the LR does require expert testimony. I think everyone would agree that's probably a good thing. Came from a court in Montana. However, a statistician need not appear. A DNA analyst is quite qualified to testify to an LR with a sufficient foundational predicate that we talked about. Education, training, or experience will do it. And this court recently in Maryland came to that conclusion. However, when it comes to questions of relevant and competing questions in a case, and not the underlying principles of math or science behind formulas, relevance is not defined or decided by scientists and statisticians. That is the province of the court. And some of you may be aware of the Jenkins decision. Was cited by many subsequent courts and is very influential on that particular point. In terms of statistical uncertainty, many courts have said statistical foundations and probability estimates go to weight and not admissibility. And specifically, the application of the LR goes to weight and not admissibility, according to these two courts. The LR has specifically been applied to mixed DNA samples when contributors cannot be distinguished. That's been ruled to be appropriate in the state of Massachusetts. An application of the LR to drop out alleles and drop out loci is permissible, and with regard as well to major and minor contributors in these two cases from Massachusetts and Arizona. In terms of assumptions and balanced propositions, in this case from Massachusetts, the defendant argued that the expert's reliance on unsupported assumptions was not persuasive. Again, Dr. Weir was the expert in this case. He presented statistics for both possible scenarios. I don't know what those were, but he, according to the court, did not assume anything. Rather, he presented statistical analyses for the full range of possibilities. And interestingly, the court adds that the Commonwealth presented only a calculation based on the assumption that the victim's DNA was part of the sample. The defendant's argument would perhaps carry more weight. However, because the expert did present the exact same calculation covering the countervailing assumption, the presentation was complete, and the expert didn't rely on any particular assumption or finding to whether the victim's DNA was or was not part of the sample. There are some interesting cases about what I call legal sufficiency to support the verdict thus far in the young life of LRs in the American system relative to DNA. And in these three cases, two from Louisiana, one from Texas, some pretty impressively rare numbers were proffered, and these courts found that those numbers were more than sufficient for a conviction. And these were DNA evidence alone cases, so more or less your cold cases where you don't have any leads, but you do have DNA. These are LR numbers that these courts found were enough, standing alone, to support the verdict. This is an interesting case from the state of New York. This is a New York Court of Appeals case. Physical assault case. The victim couldn't identify the attackers. However, he said he was assaulted by about 20 Hasidic Jewish men. The victim's sneaker was removed by one of the attackers and thrown on a nearby roof, and for some reason it wasn't recovered for 6 days. The results were that a non-deducible mixture was recovered from the sneaker. The location wasn't specified, and this was a case where FST software from New York was used. The LR in one set of propositions was 133 times more likely if the mixture was the defendant and the victim than if it had derived from the victim and an unknown, unrelated person. Interestingly, there was a second set of propositions that was 695,000 times more likely if the mixture was from the defendant and an unknown, unrelated person than if from two unknown, unrelateds. Interestingly, the court found that the evidence was legally sufficient to establish guilt beyond a reasonable doubt. However, on appeal, that same court recognized that a Caucasian population database was used and the defendant was a member of the Hasidic population, and the population data, according to the court, failed to take account of the genetic history of the defendant. Some of you may know there's a long history of litigation of this in terms of databases in the state of California. Just recounting the facts here, not commenting on them. The court found that the LR was only 133, a relatively insubstantial number. But the court completely ignored the second set of propositions that included, under HP, the defendant and an unknown, unrelated person on that shoe, as opposed to two unknown, unrelated persons. That LR was 695,000, not even mentioned by the court, and only the 133 was mentioned. The court found that guilt was not established beyond a reasonable doubt based on its independent factual review power, and this may be unique to the state of New York, I don't know. This is not the law in most states, but the court found that the guilty verdict was against the weight of the evidence, even though there was sufficient evidence to support the verdict, operating as a 13th juror. So, interesting case from New York about LRs. In terms of factual foundation and explanation for an LR, a couple interesting opinions to take note of. This is a concurring judge on the Pennsylvania Supreme Court in an opinion where he said that he has concerns regarding the use of an LR in evidence. And his concern apparently stemmed from the fact there was no testimony to show how the statistical analysis was achieved, and he thinks or thought that prudence dictated that there must be a record developed demonstrating the methodology and the techniques and how these numbers were generated to arrive at that conclusion. The flip side of that point of view in a California case a couple of years ago was that the defense claimed that the LR had no evidentiary value because the expert didn't explain or display how the LR was calculated. Basically the same argument, and the court said, wait a minute, this is opinion evidence that reasonably relied on by experts in the field, and if you'll recall the federal rules, the onus is on the opposing party to bring out the deficiencies or to discover and expose the basis for those opinions, whether they're well-founded or not. Posing up here with some conceptual confusion about the LR is another interesting case from the state of New York. And by the way, if there's anybody out there who's listening in who has had some personal knowledge or involvement in any of these cases, I'd be interested to hear from you and kind of get the backstory about some of these. This is one case, Ram Sarin from New York again, 2016 case. Husband was convicted of second-degree murder of his wife. There was a blood stain on shirt worn by the defendant, and there was a mixture of profiles. The LR and the evidence was that it was 1.6 quadrillion times more likely the donors to that stain were the defendant and the victim, rather than if the evidence came from two random unrelated people. The court stated, quote, not enough alleles or data from the DNA exists to say conclusively that the victim's DNA was present as a minor contributor. And in closing argument, the prosecutor, according to the court, repeatedly mischaracterized the expert's testimony and the DNA results by stating multiple times that the victim's DNA was present in the sweatshirt. And as you recall, the mixture was 1.6 quadrillion times more likely if the evidence contained the defendant and the victim. But the court said that it's just not enough, given the qualified nature of the test results. Defense counsel's failure to object during summation deprived the defendant of effective assistance of counsel. The conviction was reversed, but interestingly, silently later reinstated by the New York Court of Appeals, and it never quite fully explains why it reinstated that conviction. But it did reinstate that conviction, and this alleged mischaracterization by the prosecutor was the reason the court gave for reversing that conviction. So there's something going on behind the scenes there that isn't fully explained, but this is an example where we've got an incorrect assumption of discrete genotyping by a court, and in fact this is probabilistic in nature, and the court apparently had a difficult time wrapping its head around that. Some more conceptual confusion here. A defense attorney on behalf of his client maintains that the state's expert gave contradictory testimony about the initial match. CPE was at issue here, and 80.5% of the population were excluded. And LR was applied as well, and it was 14.3 million times more likely. The evidence originated from the prosecutors, or consistent with prosecutors' proposition than if if a random person had contributed to it. So the defendant argued that the testimony was internally contradictory or reconcilable with the physical evidence, and the court didn't buy that argument and realized the distinction there and affirmed the appeal. Finally, transposing the conditional, there's been a lot of attention brought to this during the course of this series, and I want to reiterate that this is a problem and challenge. That's an interesting case from the state of Washington, a robbery prosecution where a mid cap was left behind, and the proposition was for the prosecution 140 times more likely than the competing proposition. offered by the expert. And a number of interesting things happened here. The prosecutor used a coin flip analogy in summation. And among the folks who transposed the conditional were not only the DNA analyst, but the prosecutor and the court and the appellate attorney in the papers on appeal. So the transposed conditional ran the table in this case. Everybody got it wrong at some point if you look through all of the paperwork in the case. So needless to say, we have a lot of work to do in the area of education and training in terms of the likelihood ratio, what it means conceptually and what it means practically, and then also how to state it correctly. And also the fact that this is a ratio of two probabilities, and it is not a probability itself, it is a likelihood. So that is territory that is ripe for lots of training and lots of inventive ways, as we've been discussing in this series, to properly, while we correctly articulate this concept to the jury, we need to keep working through this so that we can finally hit a sweet spot, hopefully, where, as Dr. Buckleton says, we may not get it perfect, but we're going to get it right much more than we're going to get it wrong. I will conclude by the words of that famous Scottish English empiricist David Hume, who was a contemporary of the Reverend Bayes, when he said, "A wise man proportions his belief to the evidence," and good advice for not only the DNA analyst, but for all of us to live by. Thank you very much. Those are my thoughts, and I'll turn it back over to Tamara.
All right. Thank you so much, Ted. I really appreciate all the work you put into getting this information together for us to put it all in the context and perspective of the law. Thanks so much, Ted. And with that, I would like to move on into our next speaker, Klaus Fluten. We will proceed with that lecture and then wrap up the series with the leftover questions that we have. And so Klaus, please feel free to start sharing your screen when you're ready. Thank you.
Okay, I'm sharing my screen now. I'm trying to. Okay, I think this works. So thank you for the introduction. So I'm going to talk about a topic that has interested me for a long time, the interpretation of DNA database matches. That came up. I think somebody had a question about that during one of the previous sessions. And this is something that I've recently been doing some work on together with Ronald Meester. So I think this is a nice opportunity to talk about that. So let me first introduce it by going back to the old DNA database debate. So in the 90s or 80s maybe even, when DNA databases started to grow, there was some concern as to how to deal with DNA database matches as compared with the classical probable cause cases. Because in a DNA database, you have very many persons who have their DNA profile registered in there, and then people started to worry whether or not the evidence would be the same or worth less or maybe more than compared to a probable cause case, where a probable cause case I understand to mean that you first identify a suspect, that suspect turns out to yield a DNA match, and there are no other comparisons done with additional individuals. So we have this match with the suspect and no other people that have their DNA checked, as compared to a DNA database where you find a suspect in a DNA database with lots of people in it. So a debate initially arose because there were two quite seemingly opposing intuitions. So let me say that C I will take to represent the actual trace donor. So C could stand for criminal perhaps, although I'm not concerned with that aspect. I'm just wondering whether a person could be the trace donor, the donor of the DNA in that trace. And then I use the label S for suspect for a person who is a unique individual in the DNA database that has the same profile as C. So one way of reasoning is that, well, we have a match between the trace and the person of interest, the suspect S, and that is the same evidence as in a probable cause case. And then in addition, we have many other persons that are excluded as source of the trace. All the other people in the DNA database who turns out to have a different profile, of course, are no longer candidates for being C. So that means the evidence against S is strengthened compared to the probable cause case. Well, that seems pretty convincing, but on the other hand, there was a second intuition that said, well, of course, we are focusing on S now because this person turns out to be the unique person who has the same profile as C, but we would have been interested in anyone who matches. So it has to be relevant somehow that we did many comparisons, and many comparisons gives us more opportunity for coincidental matches. And we need to take that into account in the evidential value. So these are two very diverging views, and it's perhaps not surprising that the proponents of these approaches came up with different likelihood ratios that they advocated. So the people who were convinced by the first approach, they basically said, well, we're going to use a likelihood ratio of 1 over P, where P is this random match probability of the trace, the likelihood ratio that we would use in a probable cause case. And that would then be a little bit of an understatement of the evidence, because the database search, they said, is a stronger evidence than the probable cause evidence. So if we just use a probable cause likelihood ratio, then we should be on the conservative side. Whereas the proponents of the second approach, they said, well, you should use a likelihood ratio of 1 divided by n times P, where n is then the number of individuals that you have searched against with the database size. So, and of course, this makes quite a difference with databases containing millions of individuals, possibly. And this 1 over NP is actually a likelihood ratio for the hypothesis that this trace donor is in the database versus is not in the database. It's not a likelihood ratio for the hypothesis that the trace donor is a suspect versus is not a suspect. Well, then there was considerable debate, quite heated debate over which likelihood ratio one should use. And nowadays, most people have actually adopted the first approach, and they would report a likelihood ratio of 1 over P instead of a likelihood ratio of 1 over NP. But I'm going to, in this presentation, analyze these ways of reasoning, and I will argue that both views can actually be correct simultaneously. So first, let me mention that we're going to look at different types of database searches because we could have different types of search that we do. So I'm going to distinguish between a cold case search, what I would call a cold case search is perhaps the type of search that people have in mind when we have this debate. We're searching the database for a trace donor, and we have no clue as to who could be that trace donor. So we do not have a specific person already in mind prior to the search for being the source of the trace. But now that the databases already exist for quite some time, you could also have a probable cause search. So police have identified a suspect. It's not necessary to take a reference sample from that suspect because the suspect is already in the database. So the suspect happens to be in the database, and then one way of doing the comparison is just searching the whole database with the idea that we can then confirm this suspicion and at the same time eliminate any others of the others from the inquiry while we're at it. So these are, of course, searches that can give you the same result, single match, but with different, let's say, reasons reflected in prior probabilities before you do that search. And then the last one that I'm going to consider is what I would call an anonymous search, which at least in Europe happens a lot between databases of different countries. So one jurisdiction would send out a trace to the database of another jurisdiction, and that database will just confirm that it holds a matching profile, and also saying which of the loci that you have actually sent have been compared because maybe they use different sets of loci and so on. So we can then compute P, but there is absolutely nothing else. So there are no personal details on the matching individual. It just confirms, well, you sent us a profile of a trace. We also have that profile in a person, in one person. So I'm going to set up a small framework in which we can think of all these searches at the same time. So what I'm going to first do is to concentrate on what is ultimately, I think, of interest, namely the probability that the search results in finding the actual trace donor. So let me denote by ES the search result that some person, S, is the only match. So what we want to know is the probability that this person is actually the trace donor, given the database evidence. So by probability of S equals C, I mean the probability that they are the same individual, that we found a trace donor, and S is not equal to C. Of course, that the suspect happens to be somebody who gave a coincidental match. Conditional on the single match being with S. Now this thing that we want to know, this quantity that we want to know, the posterior odds on S being equal to C, we can actually rewrite that as a formula involving three probabilities. So these posterior odds are mathematically the same as 1 over the match probability PS. I'm going to explain all these three separately in a moment. But what I want to say is that on the left-hand side is what we want to know, the odds on the match being with a trace donor. And on the right-hand side is what we then need to know to get these odds. So there are three things that we need to know. And we haven't introduced anything additional until now. So no population or anything else. On the right-hand side, the things that appear there are the suspect, are the trace donor C, the database. And the only thing that we additionally need is the rarity PS. So let me discuss these three ingredients one by one, what they actually mean. So the first one, the probability that C is in D, so this mathematical notation means the probability that the trace donor is in the database prior to the search. There is no conditioning on the outcome of the search. So this would mean, let's say, the suitability of the database, the probability that the database contains the trace donor prior to the search. If this probability is high, we are, of course, more interested in actually carrying out that search than if that probability is low. And this probability to contain C, you can think of that perhaps as the coverage of the offender populations for the case at hand. So how likely is it that, in this case, the database is going to contain the trace donor? That's the probability that C is in D. And then in the formula, you will see this element sign crossed out, meaning that we're talking here about the probability that the trace donor is not in C. So if nothing else changes on the right-hand side, if the only thing that we vary is this probability that C is in D, if we take a larger database and we increase the probability to have the trace donor in it, then of course the probability that the trace donor is not in it will decrease. And that means that the odds on the match being with the right person will increase. So the less room there is outside the database, the higher the probability that we found the right person when we have a single match. So that's the first ingredient. If we want to assess the posterior odds on a database match, we need first to know how suitable is the database for that purpose. How could we possibly give a value to that number? Well, one thing we could do for a cold case search is use the match rate that we have realized thus far on that database. So if we know that we have searched very many traces and compared them with that database and say 40% of those traces gave a match, then we could use for the probability to contain the trace donor 0.4 as some kind of ballpark estimate, assuming that almost all of those previous matches have actually been with the correct individual. Now, it's not unusual for databases to be so old and so large that these odds on containing the trace donor or on giving a single match are fairly close to even odds, say within one order of magnitude, so that there would be between 10 to 1 in favor or 1 to 10 against. And this would be something we could use in a cold case search where we have absolutely no further information on the case. In a probable cause search, there apparently is some more information. And if that information is relevant for our assessment of the probability to contain the trace donor, we should take that into account. So for a cold case search, perhaps we could use this match rate, and otherwise we have to think about what the information that we have means. Well, the second ingredient that we need, of course, is a familiar one. It's the random match probability for S. So I've deliberately put a subscript S here because, of course, in the database, it need not be the case, and I think it's almost never the case, that all persons are typed for exactly the same set of loci. As the DNA technology has progressed over time, the number of loci has increased, and people who are in the database for a long time, they may have fewer loci included in the database than the newer individuals. So what matters here is only the probability that this guy S would yield us a match if he were not the trace donor, and this match has been observed only on the compared loci. So what we need to evaluate here is the probability for that match to happen on the compared loci, and that is a probability PS. And of course, we would like that to be small, because the larger the PS is, so the more unlikely it is for S to give a match by chance, the larger 1 over PS is, and then of course the larger the posterior odds on the match being with the right person will be. So that's a familiar number, this PS, and we all know how to give a value to that one. And then there is the last one, that's the third and final ingredient for these posterior odds, namely the prior probability on C equals S, where there is now no information that we condition on. So this would be probability that we assign for S to be the trace donor, but without knowing yet that this guy will turn out to be the one that gives us the DNA match. And of course, the larger this probability is, so the better a candidate S is already without the DNA evidence, the better a candidate he will remain when we do have the DNA evidence. So we would like to summarize, if we like these odds to be large, we should have small random match probabilities for S, large prior odds, and a small probability for the database not to contain the trace donor. But how can we evaluate this non-DNA informed prior probability for S to be this person C? Well, again, we need to then distinguish between a cold case search and a probable cause case search. If we have absolutely no information, if we would be interested in S a priori, but also anybody else in the database, we can then suppose that we would be equally interested in all of them, and we are going to reflect that by setting the prior probability on all those people to be the same. And we already had a way of assigning a prior probability for the database to contain the trace donor by looking at the match rate that we have realized so far. And all we need to do is to divide that probability evenly across over all the people who are in the database. So we're going to set everybody's prior probability to be 1/n of the prior probability that the database contains a trace donor. And of course, when the case gets going, you will learn more about S, and the probability on C is S, and also probability on C is indeed will change. But this is a way to start. It's always very difficult to assign prior probabilities. So far what I've done is explained how we could evaluate the probability that this search has yielded us the person who is actually the trace donor. The problem now for the forensic laboratories is that this expression is not in the form we'd like it to be in. We'd like it to be in the form of a likelihood ratio multiplied with prior odds for a pair of complementary hypotheses, so for a pair of hypotheses that are each other's negation. And that's not what we have here. on the right-hand side, we have hypotheses, the prior probability for S and the prior probability for the database to not contain the trace donor. On the left-hand side, we have the posterior odds on the suspect being the trace donor. So they're not in a way that we like them to be in, but of course we can just force them to look that way. If we look on the right-hand side, we can either force it to look like a likelihood ratio times prior odds on S is C, by just introducing the term that is missing, namely in the denominator, the probability S is not equal to C, and then canceling it out in the numerator again. So then we can just put in that term, and what is left out, what's left in the middle has to be the likelihood ratio. Or we can choose to put in the prior odds on hypotheses that the database contains or does not contain the trace donor. If we would do it in the first way, by writing it as a likelihood ratio times prior odds on the trace donor being the suspect, then we're looking at the odds on the matter of interest after the search. The interest now lies in whether or not the trace donor is this suspect that was uncovered by the search. But that is not what we were initially doing in a cold case search. If we would express it as likelihood ratio times prior odds on the database containing the trace donor, then we have the matter of interest prior to the search, because we were not searching the database because we were hoping that S would pop out in a cold case. So we were searching the database because we were hoping that it might contain the trace donor. We didn't have anyone specific in mind. So that was the reason to carry out the search. It was a matter of interest prior to the search. But then, of course, our focus has shifted now that we have this match, and now we're interested in whether or not this identified suspect is a source of the DNA evidence. But on the right-hand side, each of these hypotheses comes in just once. And we have to introduce the second one sort of forcefully. So the problem is that neither way of writing is a very natural way of doing it. Because if we take one set of hypotheses, we consider what we were initially investigating, but not what we focus on after the search, or the other way around. But mathematically, it's fine to do that, but we must keep in mind what's going on if we want to understand this a little bit. So let me give an example of the three types of searches. So suppose I have a database with 1 million individuals in it. So n is 10 to the power 6 is 1 million. We search it with the trace. We get this suspect S as a match, and the probability that he would match the profile, if not the trace donor, is 10 to the minus 9. And we know by previous experience that about 40% of the trace donors are actually findable in that database. So the posterior odds now, we need to think about these three numbers. We have PS already. The probability that the trace donor is not in the database is 1 minus 0.4, so 0.6. And then we need a prior on this suspect that how likely would we think it was him prior to the search. So in this cold case search, we have no way to distinguish between database members, so we use probability 0.4 that we have now to divide over 1 million people, so this is 4 in 10 million. So how can we, so then we can compute these posterior odds with these three quantities, and that they evaluate to about 667. And if we express them as a likelihood ratio times prior odds on the matter of interest now, namely whether the trace donor is a suspect, then we can write this as a likelihood ratio of 1.7 billion times very small prior odds. So how can we think of that? Well, the odds on the trace donor being this guy S, prior to the search, they were 4 in 10 million. And now with the database match, they have increased, so it's become 667. So we write it as a very large likelihood ratio multiplied with a very small prior odds. The second way of writing these posterior odds would be to write as a likelihood ratio for the database to contain the trace donor times the prior odds on that. So the prior probability was 40%, so the odds are 40 versus 60%, which simplifies to 2/3. N times P, with N a million and P 1 in a billion, is 1,000. I mean, 1 over NP is 1,000. And this we can interpret as follows. So we can say now, well, the odds on finding the trace donor in a database, they were assessed as 2 to 3 before the search. And now that we have this match, they are 667 to 1. And additionally, this guy S is the only candidate left. So not only has the probability that the database contains a trace donor increased a lot, but also internally inside the database, things have changed. Before the search, everybody was a candidate, and now all the probability of the database focuses on this particular individual S. So this way of writing the posterior odds as likelihood ratio 1.7 billion and very small prior odds gives us, and it has to give us, the same result as writing it as a likelihood ratio of 1,000, but now with very large prior odds. So if we focus on this suspect that we uncover, we have very strong evidence by construction, basically, because we're going to focus on him because he gives us a match. In this example, the likelihood ratio is more than 1 billion, but this is compensated by very small prior odds, which represents that the case against this suspect is very weak without the DNA evidence. If we wouldn't have had that DNA evidence, we wouldn't have a case against S at all. If we focus on the database, we have much weaker evidence, but that's because we are trying to prove something that is much more plausible. It is quite plausible that the trace donor can be found via the database. That has a probability of about 40% in this example. But both of these routes enable us to find the posterior odds that the person that we found in a database is actually the trace donor. There is mathematically no preference of one route over another one. So if a choice has to be made, it should be for non-mathematical reasons, because from a mathematical point of view, these two routes are both open to us. So this was a cold case search. Let me now move on to a probable cause search. So still we have that database of 1 million individuals, but now we have an already identified suspect, and that person is also in the database. And that person is the only one who matches. There are no other matches, and we again have this profile 10 to the -9. So we basically have the same outcome of the search, but this time the match is with a suspect that has been already identified. Or we could alternatively think of it as a suspect who was found through a cold case search, and now we have uncovered more evidence. So what can we do then? Now the posterior odds, they still rely on the 3 key probabilities that we need: the random match probability for S, the probability that the database doesn't contain the trace donor, and the prior probability that the trace donor is this guy S. But now, the random match probability hasn't changed, but the latter probabilities have changed. In a probable cause, suppose you have good reason to have a suspicion against S. Perhaps we could say the probability that he's a trace donor is already 0.75. So let's say that for the sake of this example. So the probability that the database contains a trace donor, of course, with S being in a database, is at least 0.75. And with the remaining probability that is not C, so 25%, then we can say, well, we use the 40% of the cold case search again. If it's not S, we say we don't have a clue. If we do that, then the probability to find the trace donor in a database is now 85%. So much larger, of course, than in the cold case search. And if we now look at these two rules, then they coincide much more. The posterior odds, we can fill in the numbers that I've just given in this example. And then the posterior odds on S being the trace donor are 5 billion. So they are much larger than in the cold case search, even though we still have single match with the same random match probability. They are larger now because the situation is different. They are now 5 billion, and if we would express them as a likelihood ratio times prior odds on the matter of interest now, whether the trace donor is S, or as likelihood ratio times prior odds on the matter of interest before, whether or not the database contains a trace donor, then these two expressions give us much more similar answers than in the first cold case example. The first one will give us a prior odds of 3, because the probability that S was the trace owner was assessed at 75%, so 75 divided by 25 gives us prior odds of 3. And then the likelihood ratio is 1.7 billion, as it was before. And in the second route, we have 5.7 now for the prior odds of the database to contain the trace owner, and this is mainly due to this suspect S. And the likelihood ratio is now 0.9 times a billion. And you see that this is much less difference than it was with the other cold case example. Why is there much less difference? Because S is now not at all an ordinary database member. S was the person of interest already prior to the search. And then the last type of search, we have this anonymous search. So C, we don't know who that is. We have his DNA profile. We send it to a database D. And that database returns the information, hey, I also have this profile. And I have so many loci of being able to compare it on such and such loci, and this is a relevant PS. But nothing further is disclosed. There is no information on S. In that case, you can show that the resulting posterior odds are the same that we would have had with equal prior probability on the database. And then we get basically the results from the cold case search back. And again, we can shift factor n between the likelihood ratio and the prior odds. But this time, because all we know is that we've sent it to some external database, and that database told us, yes, I also have that profile, but nothing else. Then it may be more in line with intuition to just keep in mind why we did that search, which is represented by the odds on that database to contain the trace owner, and on what came out of it, namely how many persons were compared and what was the what is the probability that the one person who matches would match if you were not the trace owner. Although nothing would prevent us from using prior odds on that unknown individual as well. I would say maybe now it would be more in line with intuition to think about the database as a whole, but everybody can do what he or she likes with that. So, but now comes the problem, what should we report? So forensic laboratories have chosen to, or they are obliged to report the likelihood ratio, not the posterior odds. We've seen the posterior odds are not the problematic quantity here because they can be computed without any ambiguity. But for the likelihood ratio, the choice that we make for computing this posterior odds is very important in what the likelihood ratio will be. So there are basically two candidates for a likelihood ratio, 1 over P and 1 over NP. And I'm going to discuss what happens if you choose for either one of them. So at least in a cold case search, you can choose between 1 over P and 1 over NP. You can only choose for 1 over NP if the person who comes out was an ordinary database member that you knew nothing special about, as in a cold case search. So choosing for 1 over the profile probability has some advantages. It's very easily applicable. You give the same number whether or not it's a probable cause case or a database search. You don't need to assess any prior probabilities. It's a conservative evaluation of the evidence for the hypothesis of interest now, namely whether or not that trace owner is a suspect that we found. But it has a single disadvantage, which can be a very important one, namely that the prior odds must not be forgotten, and that the likelihood ratio should not be interpreted as posterior odds. In the cold case example that I gave, the likelihood ratio was over 1 billion, but the posterior odds were less than 1,000. What would happen if we would report 1 over NP? Well, it has a couple of disadvantages and a couple of advantages. One disadvantage is it is less easily applicable for many reasons. One being that this number changes over time, the number of persons in the database, so you would have to look up the number every time. It only applies for cold case searches. But an advantage is that both the likelihood ratio and the prior odds that you then numerically get, they are more sort of easily digestible numbers. They are much less extreme than in the 1 over P case, where you have to compensate for very strong evidence with very small prior odds. That is very much less the case with this approach here. So another advantage is that, as I said, in many jurisdictions, the probability for a database to contain a trace owner, the odds on that are not so far from even. And if they would be even, then 1 over NP is actually the posterior odds as well. So in that case, if the likelihood ratio of 1 over NP would be misinterpreted as posterior odds, no big mistake is made. I mean, a conceptual mistake is made, but no major consequences will follow from that. Of course, the disadvantage is it only applies to cold case searches, because we need to know that the probability that this person that we found was 1 over the number of people that we compared. So in this cold case search, we can argue for both 1 over P and 1 over NP as likelihood ratios. But both of these ways are, to some extent, artificial, because we have to write these posterior odds as likelihood ratio times prior, whereas they do not naturally factor like that. So, and this is basically a self-inflicted problem, because we've made it our task to give a likelihood ratio. And in this particular situation, there isn't always a single best choice for that. I mean, there are 2 good choices, and both have their advantages and disadvantages. You can either focus on the question that has been asked to the laboratory, namely, can you please check whether the database holds the donor of this trace? Or you can focus on the question that comes next, namely, can you, what's the probability that this person that has been found via the database is actually the trace donor? And both of these questions at some point of the process have played a role. So 1 over P is easier to implement, but if the likelihood ratio is not correctly interpreted, it entails a larger risk of errors. So I would say proponents of either approach, this debate is not entirely settled, there's still a little bit going on. Proponents of either approach, in my view, they are usually correct when they claim that their likelihood ratio is appropriate. But they are usually wrong when they claim that the other one is not. And I would say the debate should rather be about something else, namely, should a laboratory be allowed to assess prior probabilities? And if not, who should do that? Because if we are not going to use prior probabilities, then how is a decision going to be reached then based on the likelihood ratio alone? What alternative do we have if priors cannot be formulated so easily? And should a laboratory, or perhaps an expert, be able to give an opinion on posterior probabilities as the result of prior probabilities and likelihood ratios? So one pragmatic solution that I have been sort of thinking about is that, well, if you think about this problem, this is not an easy problem. This has lots of subtleties in it. But people who are trained in probability and statistics, either the likelihood ratio of 1 over P or 1 over NP, if you state carefully what the result of the search was, what the stated hypotheses are, and what the likelihood ratio is, then somebody who receives that information, and if that person has a lot of training in probability and statistics, that person will be able to go forward to the correct inference, both with 1 over P or 1 over NP. For a trained individual, this is not a problem. But for a person who is not trained in probability and statistics, they will make certain mistakes more easily. So one very common mistake is to understand the likelihood ratio as the posterior odds. And in that case, it becomes more dangerous. Moreover, I don't know whether or not judges or jurors would use priors at all, and whether they apply Bayes' rule or that they rather act on the basis of the likelihood ratio itself or some verbal equivalent of it. So to avoid undesirable consequences, one could say, well, I'm going to give the likelihood ratio. If I can choose between different likelihood ratios that both lead potentially to the right result for an informed person, I'm going to give, for safety reasons, the likelihood ratio that is closest to the posterior odds, given the information that is at that point available. And which one would that be? Well, the examples of the cold case and the probable cause case search, we had a database of 1 million individuals. We had a suspect who matches with a random match probability of 1 in a billion. In the cold case, this gives posterior odds of 667. In the probable cause case, the posterior odds were over 1 billion. So in the cold case, the posterior odds on this person to be the trace donor are 667. But the likelihood ratio for C equals S is over 1 billion. The likelihood ratio for C, the trace donor to be in a database, is 1,000. In the probable cause case, the posterior odds on this person being the trace owner were much larger because this was already a good candidate. The likelihood ratio for C to be the suspect S that was already a suspect and then turned out to be the only match is over 1 billion. The likelihood ratio for the database to contain a trace owner is a little below 1 billion. So in the cold case, the likelihood ratio for the thing that we were investigating, namely whether or not the database contains the trace owner, is closer to the posterior odds. And also in the probable cause search, the likelihood ratio for the thing that we were investigating whether the trace owner was this suspect of ours, and we were going through the database just for convenience, basically. But we already had this person in mind. And in that case, the probable cause likelihood ratio, the likelihood ratio for C trace owner being S is closer to the posterior odds than the one for the database to contain the trace owner. So in the cold case search, if we would interpret a likelihood ratio of 1 over P as posterior odds, that would be a likelihood ratio of 1 billion. That would be very wrong because the posterior odds are only 667. If we would interpret the likelihood ratio of 1,000 as posterior odds, that would be much less wrong. Confusing 1,000 with 667 is not a very big mistake compared to confusing 667 with 1 billion. And in the probable cause search, the likelihood ratio for the hypothesis that we have found a trace donor C being equal to the suspect or not is closest to the posterior odds. And the database as a whole is much less relevant because we already had this guy in mind. And of course, the match increased our suspicion, but the other people were from the onset much less relevant. So we could perhaps formulate it like that. I'm going to have to look at the time because I actually don't have a watch and I don't know how long I've been speaking for. Okay. I'm almost finished with this presentation. So in a cold case search, we could say, well, the question that comes in is that we have an item. The request was that please generate a DNA profile from item X. Use that profile to search for its donor in the database. And no specific individual has been mentioned to warrant any special attention. Then a result would be that from that item X, we obtain a single source DNA profile. We compare it with the database. At the time of the search, the database contained 1 million profiles, and a single match with database number S has been found. The probability for S to produce a match, if not trace donor, is 10 to the minus 9, so 1 in a billion. What's the consequence? The search result is 1,000 times more likely if the database contains a trace donor than if it does not. And furthermore, the search result implies that S is the only person in the database who can be the trace donor. So then we would here in the consequence use this likelihood ratio of 1 over NP. And in the probable cause search, we have a slightly different question. Now we have a request to generate a DNA profile from item X, again. Use that profile to search for its DNA donor in the database, again. But now, in addition, especially compare it with the profile of individual S, who is a suspect and whose profile is already in the database. Then this result confirms that suspicion. So we have, from the item single source DNA profile has been generated again. We have a single match with the suspect S. Probability for S to produce a match, if not a trace donor, is 1 in a billion. And the consequences are that the findings, they provide evidence for the hypothesis that was put in the question, namely evidence for the hypothesis that S is indeed the donor of the DNA on item X. The findings increase the odds on S being the trace donor by at least 10 to the 9 compared to what they were prior to the search result. So finally, let me revisit those two intuitions that led initially to diverging opinions on what the evidence should be. So the first intuition was that the match with S is evidence that is as strong as in a probable cause case. And in addition, many persons are excluded as source of the trace. Therefore, the evidence against S is strengthened compared to the probable cause case. That is true in the following sense. If we are going to put in more people in the database who could be the trace donor, then we increase the probability that the database contains a trace donor, we decrease the probability that the database does not contain a trace donor. So the posterior odds are going to increase if we have a matching suspect if we put in more people and no additional matches are found. So once we have this match with the suspect, other exclusions are indeed and obviously going to strengthen the case and also the evidence against S if we formulate it as a case against S. So this is true. But the second intuition is also true. The second intuition, and this pertains only to cold case searches, that one says we would have been interested in anyone who matches, and therefore it's relevant that we did N comparisons, which gives more opportunity for coincidental matches. So in which way is that true? So if this, imagine that we keep the prior probability on this person who matches the same, and also the prior probability for the database the same, but we increase the number of persons in the database. We can only do that by taking in irrelevant persons who are certainly not going to be C. Then if we make N larger, we lower actually the posterior odds if we have a single match in that larger database compared to having a single match in that smaller database. Another way to see this perhaps is to say, well, suppose we have two countries, one very large one and one very small one, and both of these countries set up a DNA database, so the large country will need many more persons in it to have the same coverage of the offender population than the smaller country. But that means that in order for this larger country with this larger database to have matches that are equally reliable, they're going to need a more powerful system to discriminate between individuals. So they're going to need a smaller random match probability PS. In that sense, the second intuition is also correct. So the reason I think that this subject is tricky is that it is a subject in which many people have an intuition, and these intuitions can be very conflicting, and yet both of them can be correct together, simply because we are focusing on the evidence, the value of the evidence, whereas it is not a naturally defined number in all cases. The posterior odds are the simple quantity here. So by focusing on the value of the evidence, we're actually not doing what we intended with this paradigm, but making our lives more difficult instead of more easy. Okay, I think that was what I wanted to say about this. Thank you for your attention. I'm going to hand over the screen to Tamara again. Thank you.
All right. Thank you so much, Klaus. Thanks so much for putting all that information together and sharing your work with us and your thoughts on that. We have one question pertaining to your talk, and I'm going to give you an opportunity to read through it as I share my screen. And actually, there's another one I just see coming in, and we'll share that one as well. Give me 1 second here to put it over on my question list. And let's see. Bear with me 1 second, and then I'll share my screen with you. But while the speakers are having a chance to review these last couple questions, I think we're going to circle back to the earlier ones from today. And I want to thank all of our speakers, not just for putting their presentations and sharing their expertise with us, but for sticking with us. We've got at least 4 time zones that I can think of, ranging from 1:30 in the afternoon, 3:30, 9:30 p.m., and 7:30 tomorrow morning. So if you all are still with us, I really appreciate that, as well as you all as participants. So let me share my screen and go over to the questions, which are here. All right, and the new ones that came in here are the last 2 here down on the bottom. But if we could go back, perhaps with the help of Sherilyn Conway, to address the questions about the context of the LR in terms of the full scale. Let's see. And then this particular question, Geraldine, if you had some thoughts on this one, whether there are any statements that are included in the report to address the potential, I think, for an adventitious support, whether when you have a low LR, rather than that being true support for a person of interest being a contributor.
I can address that. So the way that we handle our reporting is that regardless of the magnitude of the LR, we put the entire scale, and we do use the Swigdam scale, and we put that as an endnote at the end of our report. So by doing that, then if the LR is low, then it shows that there's limited support for the inclusionary hypothesis, but it also gives the context of what expected LRs might be seen in our casework. So we don't go into any detail as to how that might have occurred in that, you know, did we have a single source profile that's just very low partial, or is this just a very complex mixture? We don't go into that detail in the report, but what we would do is, if asked by either a contributor with a phone call following up from the report, or with the prosecutor as that may be taken to court, we would have the ability at that time to describe how that LR may have been obtained and what precisely those low LRs mean. So sometimes I think it's critical that we would then stress to show the whole scale to the jury or to the court to ensure that they understand the context of the result. But in other cases, I think when that LR is very high, sometimes we would just leave that, so describing that LR as very strong support. When that LR is very high, I think it's less critical maybe to go through all of the variances of what the different magnitudes might mean. So hopefully that answers the question that was asked.
Yeah, I think so. That helps. So, and the part about it, the Jameson paper, they drew conclusions about the comprehension of the number, its significance without the context of the scale. But in testimony, are you providing to the jury, you know, let's say you have an LR of 100, where that falls in the potential for values?
I think definitely. So it's left to the prosecutor certainly to ask those questions, because it's generally that's the question that comes up. So you got a result of 100, your LR is 100. What does that mean? And many times the easiest way to put that into context for the jury is to then describe the entire scale. So we try to maybe work that in as we're talking about LRs that are very low, but like I said, if they're really high, it might be less critical to describe that whole scale. But certainly when they're low especially, or when some are low and some are high, we do try to emphasize to the prosecutor that it's important to fit that information into the examination and the testimony.
That's great, yeah. I was thinking about what types of scales are lay people used to hearing about, and you know, when you go to the emergency room and they're asked to describe your pain level, it's on a scale of 1 to 10, and we generally don't think about scales that have, you know, 10 to the 28th or 10 to the 30th in terms of you know, possible numbers. So, all right, that's great, makes sense. And on the second topic that we have been discussing as speakers in the chat room as well, we've heard throughout the course a couple of different speakers, their perspectives. Joe Bright was telling us today that adventitious matches aren't errors, they are expected based on genetics. So if they're not errors, one question would be, is it appropriate to speak to them, as Mark Perlin had said in an earlier presentation, about using the adventitious match rate to describe the error rate. And David Kay, if you're still on the line with us, did you want to share your thoughts on that particular issue?
Sure. I am here, just a second. Okay. Apologies, took me a while to unmute myself. Yeah, we heard talk about sensitivity and specificity. Those are terms that are often used for categorical conclusions in, for example, a medical test. Is a disease present or not? And those are the operating characteristics. And false positives do have a meaning there. And the analog with likelihood ratios is the misclassification rate involving LR greater than 1. The cause of a discrepancy between the hypothesis and the true reality may just be inherent in the system. Nobody made a mistake per se in the way they analyzed the data, software ran as expected, but there are inherent limitations that result in the fact that the system is not perfect. It doesn't get every classification with LR greater than less than 1 correct. That's just a statistical fact. And in Dauber, to go to Ted Hunt's talk, the Supreme Court talked about error rates in this sense of a discrepancy, in that case with voice print identification, a discrepancy between what the analyst reports and what forensic scientists often call ground truth. It doesn't mean that the forensic scientist made an error in applying the test. It just means the test has its limitations. It can result in a report that doesn't correspond to what we'd love to know, which is the real truth, such as science.
Guys, I'm sorry, my call got dropped. I was just lost my connection, but I'm back in, and I'm not sure where the conversation went. Pretty much for all of David's response, but I hope we are okay. Are we okay with that?
Yeah, we're good, Tamara.
Thanks so much, Josh. Thanks, David, for stepping in and carrying that question for us. Maybe at this point now, let's just move on to the final two questions in the case. And Klaus, if you could help us with those that came in during your talk, I'll read them for the audience. In the cold case database search scenario, where your equation with factors to be taken into account that are only apparent after the hit, where in your equation would factors be taken into account that are only apparent after the hit? For example, if the presence of S on the database is due to a similar type of crime committed within the same police force area, or conversely, if it's an unrelated crime type from the far side of the country, is this part of the prior probability that C equals S? And in follow-up, how can we practically avoid the court or jury from reapplying the same factors?
Okay. Yes, I will answer that question, Tamara. But first, I'm going to give my view also on the previous question. Is it appropriate to use the frequency of non-contributor likelihood ratios greater than 1 as an error rate? And I would say you have to be very careful with that terminology. If you would say that, suppose I set a likelihood ratio threshold of 10,000, then you know in advance that less than 1 in 10,000 non-contributors are going to actually reach that threshold. So in that sense, it's an error rate. It gives you a prediction when I take many non-contributors, how many of them will by chance be genetically sufficiently similar to the trace to have this likelihood ratio of 10,000 or more. But it doesn't answer the question that we actually have, which is, given the likelihood ratio, how large is the probability that this person is actually a non-contributor? And it has even nothing to do with that at all. So I would not use the word error rate because it would perhaps suggest that given this result of 10,000, there is a very tiny probability that this person is a non-contributor. But that is absolutely something beyond our control. So for example, suppose I'm looking for the father of a person in a large DNA database. That person has only one father. But if I'm going to search a large DNA database, I'm going to find several individuals with a likelihood ratio of more than 10,000. And of course, it's impossible that many people, all of them, have a large probability to be the father of this guy that I'm looking for. So I would be very cautious with this word error rate. Error rate is on the system. If I'm going to use this system, then it's not going to happen more than 1 in, let's say, 10,000 times that I have a non-contributor that reaches that threshold. But then you're going to apply it to millions or maybe billions non-contributors. So it will happen, and you should not confuse that probability that you call an error rate with something that applies to this particular case. Okay, so far that comment. Now the question that was actually my question, that question was where would I take into account factors that come out after the hit? So I guess I will, can I briefly take over the screen to go back to my formula? Is that okay?
Yeah, please do.
Assuming I didn't get that, is that fine?
Yes, absolutely.
Okay.
Yes.
Okay. So I have actually only one formula. I'm going to go back to that formula, which is the posterior odds on the database match being with the individual that actually left the trace. So that is this formula here on the right-hand side. So what will happen if you uncover more information? Of course, P ester and the match probability is fixed. It will never change. If you uncover information that points towards your uncovered suspect, it means, of course, that the prior probability of S being the trace owner will increase. But because S is in the database, it will also decrease the probability that the trace owner is outside of the database. So this formula is actually valid under all circumstances, and you could say I've silently omitted conditioning on any other information. Then you should just condition all the probabilities on the external new information, and then they remain valid. So that's basically the answer to this question. How can you avoid information being taken into account twice? I think that's a very difficult question. I'm going to go back to the precise formulation of it. So how can we practically avoid the court or jury from reapplying the same factors? I don't think I have a good answer to that one, because it's a little bit outside the field of statistics. It's more in the legal domain. I mean, I would only be able to say something general, such as that you should always be wary that this doesn't happen by just telling them that it's important that they don't do it. But yeah, maybe that's not a very good answer. But I'm afraid that's all I can say about it.
Okay, that's good. Thank you. Thanks for stepping in. We also have Peter Gill on the line, and Peter, I welcome you to speak into the discussion. I know it's hard to go off and on, muting our lines and jumping in and out of the discussion while we're going on. But I'm wondering, this next question came in during Klaus's talk, but anyone is welcome to speak up on it. It's in the case where they were looking for the wife's blood on the husband's shirt. Isn't the more appropriate HD a mixture of the husband with an unidentified donor? Why use 2 unidentified donors?
So is that that's a question for me, right?
Sure.
So, because I didn't get the context of the question. So apparently there is a shirt of a husband, and the question is whether the wife's blood is on it. And then the question of this person who asked the question, is it a more appropriate alternative hypothesis a mixture of the husband with an unidentified donor. I would, so I have to guess actually what this case is about, but I think that, because I missed that part of the presentation, but I think what I would do, if you have a stain with a person that is, let's say, not a priori excluded to be on it, like a shirt, husband's shirt, the husband's DNA is likely to be found on it, I would first evaluate the likelihood ratio for that trace profile to contain DNA of the husband. And if that likelihood ratio is large, then I think you should subsequently always at least also do calculations where you put the husband in as a person you condition on. Because it would be very important also to know, if you do find evidence for a second person, whether that evidence actually holds up also if the husband has donated DNA to that stain. Right? That husband is a plausible candidate with a large likelihood ratio. So in any case, we need to, if only as a sort of what-if scenario, so what if the husband contributed DNA, which is very likely now, can we then find evidence against a subsequent person? So this is beneficial in two ways, because if the husband actually contributed DNA, which is almost certain then it's easier to find the remaining unknown individuals. But also, it prevents us from stating evidence against two separate persons that cannot have contributed together, let's say. So I think that any analysis where you do not condition on a person who's a good candidate with a large likelihood ratio, any such analysis would be incomplete. So that's my answer to that.
Okay. Yeah. I've seen it as well in some of our validation studies where we have a strong contributor. Let's say in this case, if it were the husband, and a trace contributor, and the person of interest, i.e. the wife here, is a non-contributor. And I've seen the combined LR there be greater than 1, and depending on how the propositions are set up. I didn't mean to, let's say, test two individuals at the same time. So to put in H1 two persons and in H2 two unknown persons. That is something I think you should not do. You should only vary one person at a time. But I think we're having difficulties with the audio.
Tamara, this is Geraldine. I can jump in here too. Okay. I think that this is in relation to a case that Ted was discussing, where there was an LR presented that was the scenario with the wife and the husband in the prosecutor's hypothesis and two unknowns in the defense hypothesis, and that LR did end up being very large. But there was no LR also presented which tested the wife independently, either by having the wife and the husband in the prosecution hypothesis along with the husband and an unknown, for example, in the defense hypothesis, which would have been one way to handle that situation, where you would look at the LR in relation to the support that it gives for the wife to be present. So I did find it interesting in the case that Ted was discussing, where the appellate court decided to, and I'm going to use the wrong legal terms here, but they decided to overturn the ruling, but then reinstated it later. So I'm unsure what the basis for the reinstatement was, but it did seem appropriate that they didn't rely on that very large LR to as support for the wife's blood to be on that shirt. So that was probably where that question came from.
Okay, thank you. Thanks, Klaas. If you can hear us, Klaas, we lost connection with you there as you were discussing this, so I apologize if we cut you off. And so for the last question, I don't know if we still have Ted with us or Geraldine, if you're able to help us with this one. There's a case cited there, but the question is, are there any other rulings that a DNA analyst does not have to be an expert statistician? Do you have anything
Yeah,
to share
I'm still
about
here,
that?
Tamara.
Oh, great. Okay.
I'm still here, Tamara. I
Okay, I'm back.
know the case that says that. That's why I included this in there, and I think every case I cited is, I believe, exhaustive for the proposition I stated. So I don't know, as of today, any other cases, state or federal, that stand for the proposition that a DNA analyst doesn't have to be an expert statistician. But I will say this, that outside the LR context, when you're talking about cases where random match probability, CPI, CPE have been challenged, the same rulings have held. In other words, the analyst does not need to be a statistician to testify to statistics or probability if there is a sufficient factual foundation laid for their qualifications.
Very good. Okay, thank you. I am going to quickly jump over to our chat field. 1 second to make sure we have gotten all of the final questions. And I believe that we have. So with that, I want to share my screen again and go to my final slide for the series, which is just to recognize all of the people that have helped us in that process as you're looking at this slide and these faces. I'm just moved by all of the people who have given us their expertise and talents and their time for this effort to help us all learn and grow in knowledge of probabilistic genotyping and calculating and using likelihood ratios and using those in court. So I am very grateful as we've moved through from statistics, software validation, communication and representation of the results, and in court, uncertainty and limitations, and then finally these special topics, the role of the examiner. And I'm just very grateful to all of these experts, as I am to Jerry Laporte at NIJ, to whom we initially proposed this idea to bring this information to you in this format, and to Josh Vickers, as well as Tyler Rabel at RTI International, who have just been wonderful helping us through to get this platform. I've had, Josh reports to us, over 1,200 unique logins, different people logging in. And I know at the FBI, we've had a group logging in as one. So there's no doubt that with everyone's assistance in this, we have been able to reach a tremendous number of people in our journey here to learn more about forensic application of probabilistic genotyping. So thanks so much for everyone that has helped to make this possible. And Josh could give us more details on this, but the lectures and the presentations are in the process of all being archived on the website. So I encourage you all to continue to visit that website for more on this particular series, future ones that will certainly be down the pike from the Forensic Technology of Excellence. So thanks so much for being a part of this. And with that, I would like to pass it back over to Josh for your final comments.
All right, thank you so much, Tamara, and thank you to all of our presenters today, Dr. Bright, Dr. Buckleton, Ted Hunt, and Dr. Slutin as well. This was a fantastic workshop series. As Tamara was mentioning, we do have the first 7 modules already archived and up on the website. Julian is going to be posting that in the chat as well. You'll also see our social media outlets, LinkedIn, Facebook, and Twitter. So make sure you're following us there to get all of the up-to-date information about this series as well as others. We will be turning this event around into our archival as well within the next week. So within the next week, all 8 modules will be up on the website and be able to be viewed, whether you would like to go back for a refresher or you have other colleagues that you feel would benefit from this. workshop series, please feel free to send that out to anyone. It is all at no cost, free of charge, just fantastic information. So again, thank you so much, Dr. Moretti, for all of your moderation for all of the events, as well as putting everything together. Thank you to the FBI for allowing you to have the time to be able to do this. Also, we always want to thank all of our attendees for joining us, not only today, but for all of the 8 modules. As Tamara said, we had over 1,200 people attend the modules. So this workshop series was just a fantastic success, and without your attendance and support, it just simply would not be possible. So thank you, everyone, for joining us today, as well as throughout the entire series. You will see down below the caption pod, we do have our survey link. It's a short survey for today's workshop, so if you wouldn't mind, before you leave, taking a few moments just to fill that out. The information that you provide is always vital, and we make sure that we want to provide the best experience possible and adjust any content in the way we disseminate that information out to you, our audience. So if you could take a few moments to complete that, we would greatly appreciate it. Again, Julian did place our links there, as well as our website, and then the archival links as well. So be sure to browse through the archivals, as well as everything else on our website at www.forensiccoe.org. Again, thank you to all of our presenters, thank you to all of our participants, and we hope everyone has a great afternoon.
Recording has stopped.